Uh, so it's time to start. So welcome all of you to the day 2 of IMSc 60. This is the first session of today's talk. And we'll have 4 talks in this session. And the first talk will be given by Professor Arvind. Professor Arvind needs no introduction. And he has been associated with IMSc for over 3 decades. And he has been inspiring generations after generations, including many of us here. I can say this especially to the TCS colleagues and including myself. I mean, not only has he been leading light in the academic area where he works, he has also been the torchbearer of the institute, one of the torchbearer of the institute. He was the director of this institute from 2014 to 2022. And I mean, he has a wide area of academic interest, complexity theory being one of them. And he will give us a talk on arithmetic complexity, non-commutative work. Over to you, Arvind.
Good morning, and thank you for the introduction. And thanks to the organizing committee for inviting me to give a talk at this really wonderful occasion, the 60th birthday of the Institute. I was recalling that I joined in 1993, which is slightly less than 30 years back. So roughly 50% of the life of the Institute I've been associated with the Institute here. So happy birthday, IMSc. So this topic, arithmetic complexity in non-commutative domains, is something that I've been collaborating with the large bunch of people who I've all listed down here. I just want to point out that Rajat Datta was a CMI student. He finished PhD from CMI, and he's in Bangalore. Utsav Ghoshal is a current PhD student at CMI, and Ramya is a colleague at IMSc. She is a faculty member here. And all the others were at some point of time PhD students at IMSc. And I've been fortunate to have a wonderful bunch of colleagues to discuss this topic. So I'm not going to talk about everything that we've done together, but just a select bunch of observations which ties together with automata theory. That's a kind of unifying theme for today's talk. So let me get started. So the central problem in complexity, as we all know, the holy grail is to separate P from NP. P is efficient, problems that can be solved in polynomial time, which basically means efficiently solved. And NP stands for a class of important problems for most of which we don't know efficient algorithms because they are hard in practice. And on the other hand, they have this nice property that they have efficiently verifiable solutions. So that's technically that's the reason why it's non-deterministic polynomial time. You can non-deterministically guess a solution, and you can then verify that you have a solution. And we don't know how to separate P from NP. So at some point of time, there's this famous person called Les Valiant. He said that let's try the easier problem first. Can we show that the permanent polynomial does not have polynomial size arithmetic circuits? So by looking at polynomial size arithmetic circuits, we dumb down the model of computation. We don't know how to deal with general computation. It's too clever. It can look at bits of a number and can do all kinds of clever things which we don't know how to handle. Suppose we restrict ourselves to just the permanent polynomial, and the reason why he considered the permanent polynomial was because counting the number of perfect matchings in a graph, or simply computing the permanent of a matrix with zeros and ones in it is as hard as any NP-complete problem. Okay, so it's in fact actually much harder. So his idea was that you take this harder problem and take a dumber model, and can you show that the permanent cannot be, cannot have polynomial size arithmetic circuits. And this was posed in 1979 sometime, and we still don't know how to show that the permanent is hard for arithmetic circuits. It requires exponential size arithmetic circuits, or at least super polynomial size arithmetic circuits. So we want to make the problem easier. So why not consider the non-commutative permanent? You make the model still dumber. So you say that the variables can't commute with each other. So you can't do clever cancellations by moving around variables. So x1 into x2 is different from x2 into x1. But the permanent polynomial still makes sense, and arithmetic circuit still makes sense because multiplication is now non-commutative. In this easier model, can we show that the permanent does not have polynomial size non-commutative arithmetic circuits? This problem was posed by a person called Noam Nizan in 1991. The problem is still open, but that's the theme, and that's the reason why we are interested in the non-commutative domain. So as I just mentioned, it's also easy to prove mathematically that proving P not equal to NP is harder than, it will imply that the permanent polynomial does not have polynomial size arithmetic circuits, which will imply that the non-commutative permanent will not have polynomial size non-commutative arithmetic circuits. So we should try 3 first. So just a quick background slide. We are the kind of things that objects we're interested in are polynomials. So the commutative polynomial ring is a multivariate polynomial ring. F is any field. You could take it as rational numbers or complex numbers. And the corresponding non-commutative object is the free non-commutative polynomial ring, where the angular brackets say that these variables xi don't commute with each other. A monomial is a word, basically. It's a string, really, on the letters x1 to xn. And this is the free non-commutative ring. And back to the familiar examples, the permanent polynomial is the first one. Non-commutative means that the variables can't be, you can't reorder the monomial. Okay, this is a particular version of the non-commutative permanent. There's more than one version. We'll just focus on this. And the other one is the standard determinant polynomial, where you throw in the sign. And we know that as opposed to the permanent, in the commutative world, the determinant has efficient algorithms. Because you can do linear algebra, you can do all kinds of things. What are arithmetic circuits? So here is a quick example. x1, x2, x3 are the inputs to the circuit. It's a directed graph, and the values flow from above to below. Plus, the plus here is the gate that takes x1 and x2 as input and computes its sum. And then it's followed, it gives its output as input to another plus gate, which takes the other input as x3. So this plus gate, the second one here, computes x1 plus x2 plus x3 in this cascaded manner. On the other side, you have a times gate which computes x1 into x3. And if the ring were non-commutative, we'll assume that it's ordered, the multiplication gates take inputs from left to right. So x1 into x3 is x1 into x3, not x3 into x1. And then you add to it the output of this plus gate, which is x1 plus x2. And finally, you multiply the two things coming from both sides, and you get this polynomial. And the order for multiplication matters when you're working with the non-commutative domain. There's a weaker model which is also very interesting for us, and that's called algebraic branching programs. So since we don't know how to handle strong models of computation, we always look for easy ways out and look at easier models of computation. So what does this do? It says basically that I can start with so it's the computation model is like a graph, a directed acyclic graph where things flow from left to right. And I can start with S, and I can say that I'll take x2, I'll multiply 1 with x2 and go to this node here. and then I can multiply it by x1 and go to this node, and then again by x1, and then again by x1. And that gives me the term x2 into x1 cube. Okay. So for every path in this directed graph from S to T, the start to the final node, I have a path that is labeled by either variables or linear forms. And what I should do is, in this model, multiply everything along that path. If it's non-commutative, the order is important from left to right, and add up all the things that you get along different paths. There is a reason why this model is interesting, and I'll come to that in a moment. But so the polynomial that is computed by this model is what I've written down here. There are so many terms corresponding to the so many paths from S to T. Each path gives a product term like this. And I should say that in the case of the circuit, the size of a circuit is the number of gates in it. You could also count the inputs. They're called input gates if you want. And here the size is just the number of nodes in the algebraic branching program in this graph. Okay. And yeah, this I've already told you. There is another important thing here which we need to keep in mind. So when we have an algebraic branching program, we can associate to it matrices, which basically have as many rows and columns as the number of nodes in this matrix. So this matrix MXI will have 15 rows and 15 columns. A particular row S, the sth row and the tth column are important because the sth entry is going to correspond to what is computed by this polynomial. But what is actually computed? What you do is you take, for every variable xi, you can associate a scalar matrix to it. Namely, you look at the ijth, the ith node and the jth node in this algebraic branching program. And for example, the two nodes that I'm pointing to, the edge is labeled by x2, and let's say this is I and this is j, then the mx2 matrix, the ijth entry, will have the scale of 1 in it, because that's the coefficient of x2. So for every variable, there is a matrix that you can associate to it. And if you give me a monomial, let's say the monomial x2, x1, 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 then you take the matrices mx2 in times mx1 times mx1 times mx1 and look at the sth entry. That will give you the coefficient of x2 into x1 cube and so on. So it's clear. So these matrices are important for us. Okay, moving on. So this is something that I told you, that the determinant, the commutative world has efficient algorithms. In particular, it even has polynomial size algebraic branching programs, as shown by Valiant in 1992, and later Meena and Vinay gave a beautiful algebraic branching program for the determinant. Also, it turns out that the determinant is typical of polynomial size, polynomial degree commutative circuits. That's like the polynomial time analog in the commutative arithmetic world, because they can all be simulated by quasi-polynomial size, I mean n to the log n size algebraic branching programs. Okay. So the determinant is not just interesting because it's ubiquitous everywhere. It's also a complete problem for the class of easily solvable problems in the arithmetic circuit, commutative arithmetic circuit world. In contrast, algebraic branching programs in the non-commutative world are quite weak. You can show, Nizam showed that any algebraic branching program that computes the permanent requires exponential size. N is the size of the permanent matrix. So this is a permanent polynomial, is the permanent of polynomial, the matrix consists, whose entries are all distinct indeterminates, non-commuting indeterminates, xij. Okay. Notice the reason why the commutative, why in the commutative world algebraic branching programs are so powerful is, of course, because of commutativity they can do much more, they can solve the determinant, and they are nearly as strong as circuits. That's what the second line actually implies. Whereas in the non-commutative world, that's not the case. For example, you take this palindrome polynomial, which makes sense in the non-commutative world. Namely, just look at all words of length n over the letters x0 and x1 and look at w times w reverse, okay, and add it all up. It's easy to see that this has small arithmetic circuits, but it requires exponential size algebraic branching programs. And that's actually because of the following reason. So people who have seen a bit of theory of computing or done a course in theory of computation would recall that palindromes are a classical example of context-free languages, which contrasts with regular languages. So just so continuing further, now I'm going to come to the connection to automata theory, the analogy with automata theory. So let me quickly recall for you a very important piece of work of Noam Chomsky, which is the Chomsky hierarchy of formal languages. It's also called the Chomsky-Schutzenberger hierarchy. So it's a foundational piece of work in linguistics, which also deeply impacted computer science. The idea is formal grammars as generational grammars. They generate languages. And so type 3 grammar, so he classified languages depending on the kind of grammars that can generate those languages, with the idea of studying natural languages, of course. And the easiest kind of grammars he could come up with are called type 3 grammars, where it basically says that I can start with something like a noun phrase or a verb phrase, capital A, and I can produce a letter, and now I'll go to a new noun phrase called capital B, from where I can produce new things and so on. But it's a kind of linear structure because I can only produce one thing at a time. And and it turns out that the languages that you could construct using such production rules are called regular languages. And the interesting thing is that they can be recognized by finite automata. So basically, finite automata are like Markov chains, memory-less structures. You see a letter and you go to a state, you don't need to remember what you saw earlier. The state is what matters. And from this state, you can see a letter and go to a fresh state and so on. So you start at a start state and you finish at a final state. All kinds of words that you can generate using this kind of a finite automaton are called regular languages. They are very important in lexical analysis and compilers. So Chomsky's work deeply gave formal structure to the design of compilers, and lexical analysis basically study of finite automata and regular languages. The next kind of grammar that he defined were type 2 grammars, where you allow production rules, where on the left side you have a non-terminal of a noun phrase or a verb phrase. On the right side you can have a string of letters and so-called non-terminals. So the languages you can generate using such production rules are called context-free languages. And they are basically, the interesting thing is that they can be recognized with using finite automata with a push-down memory. So this is important in syntax analysis of programming languages, for example. And if you turn around this production rule, you can also think of it as a circuit, because whatever is in alpha are things that are coming from below as outputs, and they produce A. Okay, they combine together to produce A. So you can view it in some sense in both directions. I'm being hazy here, but I just want to explain this analogy. The next kind of grammar is what is called context-sensitive grammars, where the context in which a non-terminal is placed is important. So I can replace A by gamma, provided it's in the context alpha beta. And it turns out that, again, there is a computation model which is linear space-bounded algorithms, which are precisely those algorithms that non-deterministic linear space-bounded algorithms, they recognize such languages. And the most general kind of grammar is free for all, and they can essentially capture all what are called recursively enumerable languages. Okay. So see, this is in the infinite domain, and just to go back and explain one point here, I can interpret this picture here, which I explained as an algebraic branching program, as a kind of automaton, because I start with at the state S. If I see the letter x2, I go to this state. Again, if I see the letter x1 and so on. So this word x2, x1 cube is something that this automaton can recognize, can accept. The only difference here in the world of polynomials is that there are also coefficients and they can cancel with each other and so on. Whereas when it comes to finite automata, it's as if we are working over the Boolean ring. The coefficient ring is just the Boolean domain. And the polynomial is just a collection of words in that case. Okay. But this analogy is very important for the few results that I'm going to show you in the next 7-8 minutes. One very important property that we'll use repeatedly is that there are very nice closure properties that these the classes of languages enjoy. So if I take a regular language and take its intersection with a context-free language, I get back a context-free language. But the intersection of two context-free languages is, alas, not context-free. On the other hand, context-sensitive languages are very robust. They are closed under complements, intersections, unions, everything. So the analogy that really helped us prove the kind of results that I'm going to quickly show you is the fact that algebraic branching programs correspond to finite automata, arithmetic, non-commutative arithmetic circuits correspond to context-free grammars. And there's also an interesting rank characterization of regular languages. So if you take the infinite matrix whose rows and columns are labeled by words, and if you take the entry corresponding to the W1, W2 at W1 row and W2th column, and if W1 concatenated with W2 is in the language, you put a 1, otherwise you put a 0, then the language is regular if and only if this infinite matrix has finite rank. And the rank of the matrix is actually the size of the smallest automaton for it. And the Nizan rank lower bound argument, I didn't tell you that it's a rank argument, but it is a rank argument. It's like a finite slice of this infinite element. Okay, so what is it in the world of polynomials, non-commutative polynomials, that is an analog of a regular language intersection context-free language being context-free? It's the Hadamard product. So if you give me two polynomials f and g, the Hadamard product of f and g is you take all the monomials and multiply the coefficient of the monomial m in the Hadamard product is just the product of the coefficients of m and f and g. Okay. And the nice thing is that just like the intersection of two regular languages is regular, you can show that the Hadamard product of two polynomials which have small algebraic branching programs of sizes S1 and S2 has size essentially order S1 into S2. Okay. And the other thing is that if f has an algebraic branching program of size S1 and g has an arithmetic circuit of size S2, their Hadamard product has an arithmetic circuit of size order S1 and S2. It's a perfect analogy of the fact that regular intersection context-free is context-free, except that sizes now matter because we are looking at finite objects and the size of circuits and size of algebraic branching programs matter. So these are our tools, and we are going to, there's just one more small thing I want to point out. So if I want to take the Hadamard product of f with p, I can do something very nice. I think of p as given by an algebraic branching program. It has variables x, y, and z in it. I can write down the matrices corresponding to these, the ones that I told you about right at the beginning. And now, if I want to compute the Hadamard product of f with p, all I need to do is, for the variables x, y, and z in the polynomial f, I just substitute these three matrices and look at the 1/4 entry, because 1 is the starting state of my algebraic branching program and 4 is the final state. And that will give me the Hadamard product of the two. So it looks kind of magical, but it's really easy because The polynomial f, essentially monomial by monomial, this algebraic branching program as an automaton is running on it, and its coefficient is going to get multiplied, like C1 into B1 is there, with the coefficient of the monomial in f. And if a monomial is not present in f, it's going to disappear because this algebraic branching program doesn't recognize that monomial. It doesn't take it from the start to the final state. Okay, good. So I can, that's the reason why I can do something nice with non-commutative arithmetic circuits. If you give me a polynomial f by a circuit and a monomial m, I can find its coefficient by designing an automaton that accepts only that monomial and evaluating the circuit on the corresponding matrices that I just told you about. In contrast, in the commutative world, if you take this polynomial, for example, which is a very simple polynomial, the coefficient of x1 into x2 into xn is the permanent of the matrix Aij, so that's hard to compute. Okay, I think I'm really running out of time, and I've not even started telling you about, so I should at least give you one example. So this is technically the definition of Vp and Vv for valiant. Vp is the valiant analog of polynomial time, and Vnp is the valiant analog of non-deterministic polynomial time. So Vp just consists of families of polynomials, each of which has a small circuit of small degree, polynomial size and polynomial degree. Because circuits in general can compute exponential degree polynomials. Circuits of size s can compute 2 power s degree polynomials. And the NP valiant class is simply like, you have these extra variables y1 to yrn, and they are like, keeping track of the solutions of the NP problem in some sense. And when you add up over all the values of y1 to yrn over 0, 1, it's like counting all the solutions. And that's what actually the original permanent polynomial corresponds to. And that's the reason Valiant was inspired to define VNP like this, which is a nice definition. Okay. So permanent is in VNP, it's even VNP complete in the commutative world, and determinant is in VP because, for example, of Mina's algebraic branching program for the determinant. And how do you prove something is complete? You need a notion of reductions. I say that if I have two polynomials f and g, g is harder than f if I can easily transform f into g, okay, because then I can use g to compute f. And the easiest kind of reductions are projections, which are just mathematical projections. You either replace a variable by a variable already used, or you replace it by a scalar. Okay. And it turns out that the permanent is VNP complete with respect to projections. Determinant is VP complete with respect to quasi-polynomial size projections. But in the non-commutative world, things get different and interesting. And I think I'll be able to tell you only one very, very quick thing. A more general notion of reducibility with generalizes projections is possible through matrix substitutions. That's what I call less than equal to mat. And for example, matrix projections are stronger than, matrix reductions are stronger than projections, because you can never project G to get two monomials because G is a single monomial, whereas I can use matrix substitutions and look at a particular entry of the resulting matrix to reduce F to G. And the interesting thing is that not only is the non-commutative permanent VNP complete, the non-commutative determinant is also VNP complete. The first one is with respect to projections. The second one has to be with respect to matrix reductions. You can't do it with respect to projections because we have a transfer theorem which says that if something in the non-commutative world was complete with respect to projections, then you can take it back to the commutative world. And we know determinants are easy in the commutative world. But with respect to matrix reductions, it is VNP complete. And how do we do it? So we want to reduce the permanent to the determinant. So that means that you have to remove the sign. But how do we compute the sign of a permutation? And I need to use matrices as substitutions. That means I really only have the power of automata with me. And automata cannot keep track of bijections, leave alone compute the sign of a permutation. So, but it turns out that we can reduce the permanent polynomial to the 2n by 2n determinant polynomial in the non-commutative world. And the idea is very simple. We will only look for certain very nice permutations. So for every permutation pi in Sn, we will define a permutation in S2n which looks like this: pi 1, n plus pi 1, pi 2, n plus pi 2. So this is the ordering. So pi 1, pi 2, pi n is the permutation in Sn that's given to me, and I expand it out into a permutation on 1 to 2n. And the nice thing about this permutation, rho of pi is a permutation on 1 to 2n. They all have the same sign, and the sign is that of rho of the identity permutation. And so it turns out, therefore, that I just need to, my automaton needs to just recognize monomials of this type. But still, how do I know that I1, I2, In forms a permutation on 1 to n? I don't need to worry about it because the determinant polynomial already takes care of that. So when I take the Hadamard product, this will make sure that I pull out only the permutations which are of the form rho pi, and the determinant will take care that everything is actually a permutation. So, and the sign is the same, so the sign disappears and we get the n by n permanent. I think I've really run out of time, and I just want to say that the analogy continues. So if I want VP completeness, now determinant is hard. So what is VP complete in the non-commutative world? You don't have to look far. Automata theory helps out. Dyke languages. So you can define Dyke polynomials and use the Chomsky-Schutzenberger theorem, which talks of the hardest context-free languages to show that the Dyke polynomial is VP complete. And we can create, using context-sensitive languages, we can create more VNP complete problems, which again are analogous, not look like permanent or determinant, but really come from the formal language, from the theory of computation setting, Hopcroft and Ullman setting. Okay. I will not have time to talk about the polynomial identity testing problem, but here too I must say that automata theory helps out in a major way. I will just rush towards the end and say something about a bunch of new results on what is the rational identity testing problem. So dealing with inverses in the non-commutative world is a totally different thing than dealing with inverses in the commutative world, because the universal free skew field has very complicated objects in it. And so you're given a rational formula, non-commutative rational formula, and you want to test if it's identically zero. So for example, just to give you a flavor of what inverses can, how messy they can look in the non-commutative world. So this is actually equal to 0, and that's called Hua's identity. So you can't simplify a non-commutative rational expression as f by g, which you can do in the commutative world, because you can move around divisions. Here, whether you're dividing on the left or right matters, and things are harder. And it turns out that if you're given a rational formula explicitly, you can do identity testing in deterministic polynomial time. Identity testing means you're given an expression, you want to test if it's identically zero. It's connected to lower bounds. No time to get into that. But the other related question is black box identity testing, where you don't see the formula, you can only evaluate it. So for example, if I put inside a black box a degree n univariate polynomial, and I want to find a point where that polynomial is non-zero, I'm only allowed to evaluate that polynomial. What will I do? I know it's degree n, so I'll take 1, 2, 3 up to n plus 1. I'll evaluate it at all these n plus 1 points. I know at one of these points it has to be non-zero if the polynomial is non-zero. But can I do it in the multivariate setting? That is the harder problem. Okay. How do I efficiently do it in the multivariate setting? So the polynomial is, the rational expression is inside a black box, and how do I deterministically check whether it is the zero expression or not? We can only do it in the special case of inversion height 2, and we only get a quasi-polynomial time algorithm, n to the log n time algorithm. And the efficient de-randomization is open. Just finally, one more result, connecting hardness to randomness. So it's known in the commutative setting that if you assume that the permanent polynomial is hard, then you can get reasonably efficient algorithms for polynomial identity testing. You can so-called de-randomize polynomial identity testing. And we could do something similar, assuming that polynomial identities in the non-commutative world have exponential algebraic branching program complexity. Okay, I think I've taken up more than my time. Thank you. Stop.
Thank you, Arvind, for a very nice talk. So the second talk of this session will be given by my colleague, Professor Saket Saurabh. He works in the area of, oh, there is some memento here, I'm sorry. For you, of course. I have to. Yeah, so the second talk will be given by my colleague, Professor Saket Saurabh. He works in the area of graph algorithms and parameterized complexity theory. He has several awards and recognitions to his credit. He is recipient of the Swarna Jayanti Fellowship, Santishwari Bhatnagar Prize, ACM India Early Career Research Award, ERC Starting Grant. He is also a member of Indian Academy of Science, Academia Europea, European Association for Theoretical Computer Science. Saket has been associated with IMSc right from his PhD days. He completed his PhD here in the year 2008. He will talk to us on his Kuti PC story. Thank you.
Thanks, Prakash. So it's always very difficult to, speak to such gatherings. So I decided not to speak too much of computer science, but I will have my own share of computer science to this. And if you are not from Tamil Nadu, then Kuti means small, and that's what it is. So a lot of, and the PC in this PC is definitely not personal computers, don't worry about it. And the picture here should become clear at the end what it is. Okay, so the principal character will be this object in my talk. So Farheen was saying that, she studied this computer science BTech, and she liked graph theory, and she moved to some biological networks and everything. I also learned graph theory, but in discrete maths, but we didn't move to, we just started to, for us, the graphs are just nodes, no names, from where it comes, it doesn't matter. And between two vertices, there is an edge, there's a link. What do they represent? It doesn't matter. So we just study abstract objects of graph. So there will be lots of graph. So this is the only definition I wanted to talk about graphs and nothing more. So actually, so what is the plan of the talk? So I'm going to give you like some glimpses of talks with my association with IMSc and viewed through the lens of science and students. And similar in the spirit which Meena said that that how much we value our graduate students and what. So it is also a tribute to all those people with whom I had crossed my path, whether they were graduate students, postdocs, interns, colleagues. And it's also a tribute to myself because I'm also a graduate student from here. So, okay, so it all started in '99, okay? And when I moved from Hindu College, where I was studying economics, inspired from Amartya Sen, but after 2 weeks, I realized that I like maths more than economics. And that is the time when I was in a, like I think some waiting list in CMI, when I was waiting that if they invite me, I'll go. So then I got a letter that I can go, and this is the place I saw students are turning down IITs for this maths institute, and I know what this institute is. It is the bigger, what is that called? It's a picture of auditorium, outside auditorium in the new place at CMI. So I moved from economics to doing pure mathematics, which is what I liked, but it was not all that easy, okay? But my real story did not start at this place or this institute. It started, and also one reason why I actually came is also because it was free education, and they were giving 500 rupees monthly salary, and in those days, trust me, 800 rupees was enough to eat and have some extra money for every Sunday lunches at Deluxe Hotel in T Nagar. And so basically, so this is where we started here. This is the J.N. Chetty Road, where the CMI was then. And I was still in early 50s, not in terms of age, in terms of weight. And, CLRS still did not have S in its title. It was still called CLR. And if you look at H. Venkatesh, who still had black hairs, real ones, then this is the earliest picture that I found of him. It's from 2003 Dakstul workshop. So this is the earliest I found. And still, we were in the millennium era, and IMSc was still in the era of Arithmetic, and I was trying to move from Arithmetic to RES. So this is my first lecture, and of my notebook of 8 August 2000, of the algorithm lecture that Venkatesh took at CMI. So this is where my association with IMSc started, with an algorithm course, and Venkatesh teaching that course at CMI at J.N. Chetty Road. And so let's move forward. And this is, I was planning to define what should I define NP completeness. So this is what Venkatesh defined. I thought, why should I take blame for anything? If this is not clear to all of you what he said, then so it be, okay? So basically, what is P? Basically, all the problems for which you can do polynomial time computation. And what was NP completeness? There are some problems for which you could not solve it in polynomial time. Example, Hamiltonian path. But more importantly, if you look here, n is a prime. You want to test. And we realized that, why? So we all gave this order root n algorithm, try. It cannot have factor more than that. And we tried, but it was not a polynomial time algorithm because it should be polynomial in the encoding length. So when you give n to the computer, you don't give it in 1, 1, 1 n times. You give it in binary, which is log n bits, right? So we were expecting to design an algorithm running time log n to the power big O of 1. And that was still an open problem then. So it was 2000, roughly end of 2000, like November, December, because it's a NP completeness, so it must have come around end. And only the 6 months later or a year later, I remember sitting in this crowd when Arvind was giving a talk on AKS algorithm, and from that S, you will hear more, I think, tomorrow. So that's about NP completeness, the problems for which we cannot design polynomial time algorithm. So it's not my fault that I did not solve primes in P because I didn't get time to solve it. That was a joke. Okay, and so as it is standard in, hardness means nothing. So these are some of the things which Venkatesh tried to teach us in last 2 lectures of his algorithm course. And So he taught us approximation of them as a mechanism to cope with NP hardness. I will define one of these two things in a few slides. And he also used the word parameterized complexity, which I will define in a minute a bit more. So we learned about NP completeness in this course. We learned about how to cope up with NP hardness. And then, so the PC in this title actually stands for this parameterized complexity, which was the last thing that Venkatesh taught in the class, which has stayed with me for last 2 decades. So this is an algorithm for vertex cover that he gave in the last lecture. Okay. So let me tell you what is the mantra of coping with NP hardness is. Okay. So basically this is what I always tell, that basically NP hardness is, there is no algorithm for this problem that solves all instances optimally in polynomial time. Okay. Now, so what is coping will mean is that let's relax each of these definitions and see what we can achieve or what we can get from there. So all instances, maybe just forget about all instances. Maybe just look at some restricted input. Maybe you don't look at all the graphs. Maybe look at the graphs that are embeddable on planes or embeddable on graphs of genus 2 or whatever. Or just look at trees. And this is also a motive of parameterized algorithms that I will define in a minute. But there's also a big branch of computer science where we forget about solving it exactly and say, hey, we still give you polynomial time. We are happy if you give us some approximation, but that approximation should be guaranteed. If you tell me that if the optimum has 10, then I will give you 20, but you should be guaranteed to give me always 20 or factor 2 approximation on every instance. So these are like guaranteed approximation algorithm, but running in polynomial time. Or you can just forget about this polynomial time and say, hey, let me allow you some more time. Can you still do much better than the naive search, which I will get in a minute. And there's also a notion of kernelization that I will not go about, which allows us to solve a bit more what you can do in polynomial time. Okay, so here's my vertex cover problem, which is a very central problem that I must tell to the audience. You're given a graph G integer k, and you have to ask a question, is there a vertex at S such that if I delete these endpoints or the vertices, there is no S left? So what does it allow is it? So what is the motivation? So I know that in computational biology, people model this vertex cover for like some interactions which they do not want or something. And there has been a lot of, what is that called, bioinformatics work has been done on this. So basically, this can model if you wanted to resolve conflicts and things like that. So this is a basic problem which has lots of motivation. But like for us, this is a basic problem that we learn in, like, this is a baby NP-complete problem in my head. Okay. And so alternate view is you want to remove k vertices. You want to remove such that there is no connections in your graph. Okay. So there is, of course, there's an algorithm for this problem, right? You try all subsets and check. But if you're only interested in checking of size k, then why do you have to check everything? You just check all subsets of size k, and you will be happy. But look at this. Like if all subsets, all k subsets of VG is so much more. But if you want, what is the main mantra or main idea is that I do not want to search over all n choose k. Can I search smaller amount of space? Like only a small number of this n choose k and still answer. So of course, the ideal will be that we only search polynomial, but these are NP hard problem. So the hoping that we can do this is not possible. So we try to say that, okay, look, it is still polynomial, but I allow you some function of some objects, like k being the size of the solution that I'm looking for, on this number of subsets that you're allowed to look for your solution, okay? And so that is the whole idea about parameterized complexity that starts. So what is parameterized algorithms? So we often assume that this k that we are looking for is reasonably small compared to the input size. So think of like n as like 1,000 and k is like 20. And then this n to the power k is way too slow. I mean, you cannot do this. But the idea is, can we narrow down this search space from this n to the power k to something smaller, something better, okay? And this is an algorithm which does this for vertex cover. So what did this algorithm tells? Hey, here is an edge. You told me that you have to pick one of these endpoints. So you pick one of these, delete it, check whether a graph has a vertex cover of size k minus 1, pick this, delete it, check with the graph has a vertex cover of size k minus 1. In both sides, you're looking for a vertex cover of 1 less size. So that's just your recursive algorithm. And if you write down the recurrence, this is what we wrote, this solves to some 2 power k times m. So that's your vertex cover algorithm from my undergraduate algorithm course. Okay, so that was an FPT algorithm for vertex cover. So what is the mantra that we try to do is that n to the power k plus 2 is polynomial for every k. So if I put k equal to 3, it is polynomial. K equal to 5, it is polynomial. But versus what we want is same polynomial for every k. So like now if you look at this is the algorithm, if you put k equal to 100, still linear. Of course, the constants are very bad, right? But this is what we mean by fixed parameter tractable, that with respect to input size are still very good, just same as polynomial, but with respect to some parameter or something, you're allowed to be exponential or you're allowed to be unbounded. Okay, so this is bad, this is good, okay? But let me quote David Johnson here. So these kind of algorithms also follows from, for many, many, many problems, those are the only known polynomial time algorithms that follows from the like big, deep theory of graph minors of Robertson and Seymour, who's like some 600 pages from 86 to 2002. Those constants are like just horrible. They're not even computable, right? So compared to those constants, if you have n to the power 100 of them, that is much better. That's all that he's trying to say. So the theory of designing such algorithms has always been there, like early 60s, 70s, 80s. People have done it for linear program. People have done for integer linear program. It's just that what was missing in the theory is that, hey, when you cannot do this, right? Like when for a problem, you cannot design such an algorithm. And that is what is the contribution of parameterized complexity or the field in itself is. Okay, so these are the basic questions that we ask. Is it FPT? Is it f of k this? Can we do better? Smaller f of k, smaller n to the power c at the same time. So these are the kind of questions that we try to address for different problems, various problems, and see what we can do or we can achieve. Okay, so now I've given you some little bit of definitions. Now it's time for me to go back. And in the summer of 2001, like as always, you know, being in CMI, what you will do, like you see everybody is going for some internship, so you also write for internship. So I came to Venkatesh and said, hey, can I do internship with you? He said, sure. And in one of those huts, he gave me this problem. It was still hut in the old days, which was burnt later. But so graph G, integer k, does there exist a vertex set S such that the following happens? G minus S has no cycles, okay? So this is why it's called feedback vertex set. And we want to find a smallest size of size at most k. So here's a graph, okay? Look, if I delete A, there is no cycle in the graph. And cycle just means you start from one place, you go around, you can come back to yourself, okay? So basically, in the language of graph theory, it is a forest. So this is the first question that I have got, and I have still from last 20 years.
Riemann surfaces, or we could look at algebraic surfaces. These are dimension 2 objects. This is dimension 1 objects. This is dimension 2, or more generally, other higher dimensional geometric objects. What is the broad theme? Surfaces, we fix their Chern class, or degree, as it's called, and then look at how the holomorphic structure varies in them, and that gets a nice algebra geometric structure. So this is yet another solution of what is called a moduli problem. Okay? So what is the theme of deformations here? So let me be a little more formal here and just define what do I mean by a family of objects. So what do I mean by this? So I say that, I look at a picture of this kind. This is in whichever category I work in. Assume that we're working in algebraic geometry category. It's a certain class of where polynomial solutions are always being used here, as our topology is what is called the Zariski topology. And so my objects are algebra geometric objects, and I look at morphisms between them. Morphisms, in every category, the morphisms carry the properties of that category. So this is an algebraic geometric morphism. And what we want when we talk about a moduli problem is that we want the inverse image for each point here to lie in our class that we wish to study. So that's what is called a family of objects characterizing a moduli problem. And these morphisms are supposed to have some technical properties which are usually something like properness and flatness. These are technical terms which essentially encode the property that you don't want, for example, the topological type to change or the topological invariants to change and similar things. So that's the kind of objects we can look at. Or we can also look at, this is for this kind of objects here. For the second kind, I fix one object. So I look at the Riemann surface X. I look at a parameter space S. And I look at this projection map X cos S to S. I'm looking at family of sheaves, a family of objects on X parameterized by S. So this is, you're expected to have some properties called flatness over S and invariants, which are what are called Hilbert polynomials, to be constant. So we are studying sheaves which are on X parameterized by spaces like S. That's the second kind of moduli problem that I'm talking about here. In either of these cases, it's a rather difficult question to parameterize these things, and this difficulty was seen early in the 50s. And what was a beautiful contribution, a rather deep contribution of Kodera and Spencer. Kodera incidentally got the Fields Medal in 1954 for several of his deep contributions, along with J.P. Sayre. And so Kodera-Spencer theory says that if I'm interested in studying a moduli problem, I'm interested in such families of objects. To understand a particular object in this family, one would like to know the local properties of this so-called moduli space. And these local properties of this moduli space can be understood even before we have a notion of the full space of the moduli problem. So this is the kind of philosophical thought that you may not, you may be interested in classifying certain objects, which is what is usually called functorial, a functorial description of the objects that we wish to classify. But we can, in some sense, understand local properties of what we wish to have even before we have the entire space. And this notion is what I call understanding the deformations of an object. So let me just quickly say what I mean by that, and a little formally here. So let's look at something like family of Riemann surfaces. So let's look at X to S, where each prime was S. So I also fix a base point S naught here. So I'm looking at a marked space S comma S naught, and I'm looking at a morphism here, which is fiber-wise Riemann surfaces. And these all are Riemann surfaces. And just as in all geometric constructions, be it in differential geometry or algebraic geometry, what we ask is, a deformation is such a family where, I say that I look at this and look at the inverse image of the base point S naught, then such a family X, which has some nice properties. For example, this is what I'll call it's a smooth morphism, which has those properties of flatness. And so smoothness would also say that the differential structure doesn't change in this family. So I look at this picture here. So my picture should be something like this. And I have a base S, which we could assume is a one-parameter base. So I have a Riemann surface in the center. A deformation is constructing such a family of objects over S. This is a very general definition. And so the family that we are looking at, a moduli problem, in some sense parameterizes some sort of an optimal family of deformations of given objects that we are looking at there. But what we wish to look at is a local property of an object. So suppose I fix this point S naught, and I want this to be isomorphic to X in my category as Riemann surfaces, for example. Then to understand the local property, what Kodera and Spencer spoke about as deformations, as what I call first order deformations of these objects, is instead of understanding the total space here, I wish to understand the tangent space to this proposed moduli space M at the given point x. So can I speak about the tangent space or expected tangent space for a good moduli problem even before I know the full solution? So what they did was, so they look at something like a trivial deformation. So this, if I look at just the second projection here, all objects are isomorphic to x. So this is what is called a trivial deformation. And we wish to classify what may be called locally trivial deformations. Just like vector bundles are locally trivial objects, or principal bundles are locally trivial objects. So you look at a trivial deformation of your object x, and then look at locally trivial deformation. So I look at, so question is classify locally trivial deformations. And as one would have it, this is like in usual vector bundle theory. A vector bundle is locally, which looks like a product of the base cross a given vector space, say complex vector space Cn. So all patching is done. We are looking at local automorphism groups of objects. And similarly, for if you fix this trivial deformation, we have to consider local automorphism groups, which allow us to do patchings. So two local deformations are said to be are patchable if you can identify the local automorphism groups of those objects. And then your deformation, total deformation, is classified in terms of what may be called sheaves, which co-cycle elements which take values in this so-called local automorphism groups. So what was proved by Codera and Spencer was that if you wish to understand the local deformation space, then there is a very natural cohomological space which is very easy to write down and compute associated to the given space x. So Tx is the tangent sheaf for that, and all your deformations locally are classified by elements which come from this first cohomology group. And this led to understanding moduli problems in rather deep ways, and several developments took place. And this is, in some sense, let me say as a summary that deformation space gives you a first order picture of a larger geometrical classification problem, and that's what is deformation theory all about. Okay. So the second theme that I wanted to talk about was degenerations. This is the other end. So you start with some smooth object. I mean, you already have some sort of a classifying picture, for example. So let me give this standard example. So this is Riemann's moduli space of Riemann surfaces of a given topological type. So that's a nice space which Riemann studied. And then one could compactify the space in some nice way, and this is called this so-called Deligne-Mumford compactification. Okay, so they even proved that this space is nice and connected. So this space has already been constructed as a moduli problem. I mean, there are several solutions to this kind of question. Modern mathematics looks at solutions to these problems from the standpoint of stacks, which means basically looking at deformation theory and trying to glue up the local deformation spaces and trying to construct a geometric object. Or we could look at putting all the objects of a given type in a big space and trying to see whether there's a natural equivalence and do what is called geometric invariant theory as studied by Mumford. So there are two ways of constructing these moduli spaces, at least popular ways of doing them. So in this case, I look at the Riemann moduli space and compactify that in the Deligne-Mumford sense. So there's a large open subset which looks like Mg here. This consists of your smooth Riemann surfaces of genus G. And at the boundary, Deligne-Mumford attach some equivalence classes of what are called stable curves, which are singular, but which still are what are called arithmetic genus G. And so this space, this total space, is what is called Mg bar here. And when I talk about the degeneration, I'm in some sense trying to construct a path from a smooth object to a singular object in this total space. So that's a degeneration, a smooth object degenerating to a singular object, a smooth object degenerating to a nodal object. So you could look at this principle. And a natural question to ask is, can one have a better understanding? This is just for the case of curves. You could ask more general problems of degenerations in projective varieties. And even as early as 1920s, Solomon Lefschetz had used beautiful ideas from degenerations like this to understand the so-called Hodge classes or algebraic cycles on these smooth objects, at least as a starting point of, in some sense, formal Hodge theory, by using such degeneration ideas. So the principle of vanishing cycle and understanding of cohomology of the smooth objects in terms of how they degenerate when you attach a good degeneration, a one-parameter degeneration of this kind. This goes back to work of Lefschetz. So taking a smooth object and degenerating it to a singular object and using, in some sense, principles of how the information at the singular fiber contains much information about the smooth object here is the principle of degeneration that one is looking at. So these two are two endpoints. I mean, deformations is like I'm looking at a corner object and seeing how much you can deform it. So trying to understand what happens in the neighborhood of a given object. Degeneration is the limit. I start with a good object and allow it to degenerate to a singular object. In some sense, the deformations of this object contains the smooth object. So these two principles have played a key role in lots of understanding of mathematics. I'm going to concentrate on two basic questions in this setting here, essentially inspired by the work of Seshadri, Narasimhan, Mumford, all the giants of the second half of the 20th century. So what is the question that I'm looking at? A question which since there are lots of physicists here, I wanted to relate it to something of this kind. So this question that I'm going to look at is so what is my basic? So let V be a finite dimensional vector space over a field K, say dimension n. Okay. So what am I interested in? A simple thing that I'm interested in is I look at, let me say, let L and K be the so-called variety or space, variety of Lie algebra structures on V. Yeah, question? Sorry. Okay, so it's a very basic question. I fix a finite dimensional vector space over a field K, for example, complex numbers, and look at all possible Lie algebra structures on it. So what is this? I mean, this is can be thought of as a subset of alternating bilinear forms on the vector space V. So this is really a subset of lambda 2 of V star, the dual tensor V. That's a vector space. As a linear space, this has got a natural affine space structure. And inside this, I'm looking at objects which have a Lie bracket, which have supposed to have a skew symmetry and a Jacobi identity, a Lie algebra structure. So I'm looking at very purely, I fix some basis E1, E2, En for my vector space V, and I'm looking at a Lie bracket mu on the vector space V determined by a point, I'll simply write it asCijr, classical physics sense, as an element of K and Q, something here. So these are the so-called structure constants, and my Lie bracket mu has the following properties on the basis. So this is summationCijr ER, R going from 1 to n. And this bracket is supposed to have two properties, skew symmetry, and 2, the Jacobi identity. And the skew symmetry will tell you something likeCijr plus Cjir is 0. And similarly, the Jacobi identity, when you unravel, will have an expression. So what one is looking at is then, now look at the automorphism group GLN, invertible matrices, is going to act on this vector space, and therefore is going to act on this, and also act on the Lie algebra structures. So we look at orbits now. So take an element G in GLN and look at a Lie algebra structure. A new Lie algebra structure can be defined as acting on the bracket operation here is going to be G acting on mu, G inverse X, G inverse Y. So this is the way in which the GLN is going to act on the Lie brackets, and we can look at the orbit of this Lie bracket, and I can take its orbit closure inside my space of all Lie algebra structures. So this space is an example of what one may be calling a degeneration of a Lie algebra structure. So this is space of degenerations of Lie algebra structures isomorphic to the one given by mu. So let me just write it as v mu as one which gives you a Lie algebra structure. So this kind of objects were studied way back in physics in 1950s by Inonu and Wigner. And they made several interesting statements about the space of such Lie algebra structures. So this is an example of a notion of degeneration of a Lie structure. One could also look at a limiting structure and ask for the deformations of the Lie algebra structure and ask what are the points which are near that. So this space of Lie algebra structures is a perfect example of where both these things come in a setting which we easily understand what we are doing here. What am I interested in, and why is my work inspired by Seshadri connected with this kind of question? Is the following problem. I'm going to combine two issues here. Okay. So I have the space of Lie algebra structures and maybe this orbit closure, which I'm looking at, which are degenerations of a given Lie algebra structure. So what am I looking at? I'm looking at a problem now. So I fix what's called a complex linear algebraic group. Examples are GLN, SLN, and all the other groups of the varying classifying types, A and B and C, and the classical Cartan-Killing classification is there. I can even assume G is what is called simply connected. So I will work with these semi-simple, simply connected algebraic groups. And the question that one is interested in is the following one. So we fix a Riemann surface and look at principal G bundles on X. Okay. So examples are vector bundles on a given Riemann surface, line bundles, as I said, that's the problem of Jacobian. All these are examples of this. This is this most general setting, and we want to classify the moduli space of principal G bundles with fixed topological types. So in the case when I'm assuming in G is simply connected, I just have to classify the moduli space here. Let me just call this moduli space as Mg. This moduli space of some natural kind was really studied by Ramanathan as a generalization of work of Seshadri and Mumford and others. So this is the most general version of this kind of moduli problem where we're looking at a general group. If you look at this problem, we are interested in two questions. When we construct this moduli space as done by Ramanathan, there's some equivalence relation, and we do what is called a geometric invariant theoretic construction. So this is a moduli space which is constructed by a quotienting construction, usually written as some sort of a quote scheme or something like that, and there is an action of some group, and this is constructed as a quotient. The moment you construct something as a quotient, it has good open subsets, which is usually called the stable locus, as studied by Mumford. And then there is points in the boundary where compactification is taking place, but there's a lot of collapsing, and in general, you could have singularities here. In fact, for G, most of the time you'll have singularities here, unless you work with some very special cases. So what is the problem that one is interested in? Two kind of questions which one could look at is, again, you go back to your moduli space Mg bar and take your smooth curve X that you have here, which is a Riemann surface here. So you could, as I said, you could look at boundary objects which look like nodal curves and ask, suppose I degenerate this smooth curve to the nodal curve, how does this moduli space degenerate? As I said, we are looking at, so one could even ask this question by taking even the so-called Jacobian of this X and ask how these things degenerate, and there's much work has been done. I think the final foundational work, a lot of is due to Oda and Seshadri. But the work begins with Igusa, Mumford, and several people who studied this question. And this kind of degeneration also has several applications in the theory of algebraic cycles and so on and so forth. So this is a very basic question. So I'm looking at something like I fix a group G and look at the moduli space of G bundles on X in a certain sense, and ask how this degenerates here when you go to a nodal curve. The other question that one could look at is, because this space MXG is singular, because as I said, we have used G objects and collapsed it, because we are doing some large equivalence relations here, what is called semi-stable equivalence relation, S equivalence class named after Seshadri. These spaces almost invariably become singular. So you could also naturally ask, because this space is singular, is it because we constructed the moduli space in a certain fashion? Is it possible to construct smooth models for this space? So that's another question, that we have a moduli space here. The boundary objects in the given moduli space, there is a good locus, and here a lot of collapsing is taking place, so it creates singularities. Usually these singularities are what are called normal singularities in the moduli spaces, because this total space here is smooth and quotients pick up only such singularities. But these are bad enough. And one of the natural questions to ask is it possible to construct smooth compactifications of this open, nice, smooth locus, which is the stable locus? And this kind of questions also have been studied. So I'll address these two as two distinct problems for looking at deformations and degenerations. So this degeneration problem and this deformation problem both have a very interesting common platform to solve it. And this is something that I have been working on for the last 10 years, inspired by with the work of Seshadri and others. So when I looked at this problem of degeneration of Lie algebras, that is, you take fixed vector space, give Lie algebra structures there and ask how they degenerate, we could ask a slightly restricted question. So my first Lie algebra that I started with here, which is the generic Lie algebra that I'm starting with, whose closures I'm taking, I could have started with something like a semi-simple Lie algebra, okay, where I want the Lie bracket to be non-degenerate and satisfying certain identities. So this Lie algebra that I start with is a semi-simple Lie algebra, and ask what are the possible degenerations of that. A related question is, I can look at, instead of the Lie algebra, I could look at the algebraic group G, which is simply connected, whose Lie algebra is determined by this v comma mu, and ask, can I construct? So each time I look at this degeneration, you can see that I'm looking at a sort of one parameter degeneration. In algebraic geometry, this kind of one parameter degeneration is parameterized by the formal power series in one variable. This is what is called a complete local ring here. So I'm looking at the following principle. I'm looking at a group scheme. That means this family of Lie algebras is captured inside a big group-like picture, but now over what is called the spectrum of a complete local ring. This is like a small disk, analytic disk, and a disk in the complex analytic sense, but algebra geometrically it will look like a curve, because we're looking at complex curves. This is a complex disk, and I'm looking at a group scheme in some sense on this. The group scheme has the property that over the open subset away from the puncture here, I'm looking at the analytic disk, and away from that, I want this group scheme to be isomorphic to the given algebraic group G, which is my semi-simple, simply connected algebraic group with the fixed Lie algebra. And I'm asking how this group scheme, can I construct what is called a flat degeneration of this group to define a global group scheme on the total space. How much time do I have? Excellent. So this study of such group schemes goes back to some gigantic work of what is called Brua and Titz, and they study these group schemes on one parameter basis, and as Mumford puts it, this work is in the scale of EGA by Grothendieck, several thousand pages in period from 1967 to 1987. The work of Brua and Titz, where they're interested in classifying such group schemes whose generic fiber is fixed and which they want to understand what sort of a degeneration is there. If the degeneration is non-reductive, can one pick up the so-called reductive part and write its root systems? And this whole study is on several of these papers, several thousand pages, and constructing these group schemes over one parameter base is a theme here. But what my observation, learning from the work of Nagaraj and Seshadri, Nagaraj, by the way, is an alumni of Faculty of Math Science, the joint work which created several new openings in this question. So we look at, in my latest work with a student from CMI, Ayesho Nidhi, Pandey. What we do, we ask a higher dimensional analog. For example, if I look at the second affine plane here and look at the regular local ring, for example, I can look at power series ring in n variables instead of one variable and look at the same kind of question. That is, if I have this on this open locus, if I know my group G, in what way can it degenerate here, what way can it degenerate here, and what way can it degenerate here. So this is a so-called point of depth 2. These two are height 1 datas like divisors. So this is like the old discrete valuation ring questions. So if I fix the data here, and if I fix the data here, can I pin down the data here? Can I construct, therefore, flat quasi-affine group schemes on the spectrum of such regular local rings? So this gives you a large class of nice smooth groups, or large higher dimensional degenerations of reductive groups or simple groups. And using this ideas, I proved two things. One is that you can construct, if you take the smooth curve degenerating to a nodal curve, by looking at what I call a two-dimensional Brouhart-Ritz theory, which I developed here, and then later on generalize it with Yoshonidi in the higher dimensional case, one can construct flat degenerations of the moduli space of G bundles on a parameter. So I can construct a geometric object which has all the good properties that Nagaraj and Seshadri and people like Faltings and others were looking at in the linear case. And this can be done for any G. And you can construct this so that the boundary has what is called normal crossing kind of singularities. So this new space that I'm looking at is generic fibers of the old MXGs and some nice describable objects. And here we require a two-dimensional Brouhart-Ritz theory. Just a one-parameter theory is not enough. The second question that I have very recently is something connected to classical work of Narasimhan Ramanan, Seshadri, and so on and so forth. They're way back 50 years ago almost. They look at a Riemann surface X, say of genus G, and then look at the simplest case, which is SL2. Look at moduli space of vector bundles of fixed determinant in rank 2. This is, as I said, a singular variety if the genus is bigger than 2. So they constructed a natural desingularization. So you have this open smooth locus of stable bundles inside this. And you can construct a scheme N sitting over Mx, SL2 here, which is so-called proper and birational. That means the open subset which is smooth is not disturbed here. There is an open subset which is isomorphic to this. And this object is smooth and projective. And this was done, strangely, only for the case SL2. And for some strange reason, it could never be generalized. And one of the themes that this is something that I worked on for my PhD on this moduli space of Seshadri's and wrote a few papers as for a part of my thesis. But the obsession with this space was always there, and as to why it works only for SL2 and why not for other cases. What's the mystery behind it? So one of the things that was always behind my mind was that SL2 is essentially spin 3, or not. It is actually equal to spin 3 because of some what is called low dimensional identification of simply connected groups. So SL2 happens to be spin 3, so I always felt that what Narasimhan Ramanan, so there are two constructions here, one due to Narasimhan and Ramanan, and one due to Seshadri, almost around the same time. There is 1978, I think. And both could do it only for SL2 case. I always felt that they did it only because SL2 was spin 3. They were not really looking at the linear case at all. So in this, as I said, the problem is they constrain themselves to work with G bundles, but in the boundary, because G bundles become equivalence classes, they pick up singularities. So can we do away with it and ask a different kind of question? So can we allow the curve to, I fix the curve, I look at stable bundles, say stable G bundles, but now I allow my group to vary in a higher dimensional Brouhart-Ritz sense as a group which varies in a different parameter space, a good parameter space which has so-called versality properties. And my boundary objects, which I'm constructing from a limit in my compactification, are no longer G bundles, what I call G prime bundles. The G prime is a degeneration of G. But degeneration, not random degeneration in a Wigner sense, but a constrained degeneration in the sense of Brouhardt's. So if I take my group G and allow it to degenerate in a constrained fashion dictated by what I call Brouhardt's and some versality properties, you can construct smooth compactifications. So the theorem is you can generalize all these things, not for the AN types mysteriously. I can do it for the BN, DN, G2, F4, two exceptional cases to adorn my theorem. And also I can throw in C3 as the new types. Of course, this case takes up the old phenomenon of SL2. This is the odd spin and the even spin, and this has the two exceptional cases. And one can use this higher dimensional Brouhardt's degeneration inspired by, as I said, all these developments. I always trace back most of these things to some theme or some thought that Seshadri used to stimulate by asking questions. And I just not able to get out of this, this problem that he was really instrumental in laying the germ of many of these ideas or seeds. And this one can do now. This is 2023. And so these two are two large phenomena where degenerations and deformations play a role. You need deformation theory to prove that this end space that we get, in fact, is smooth, because that's a local property there. And so both these are dictated by this higher dimensional Brouhardt's theory that I'm talking about, NBT. And one can think in the modern sense as applications of development of that theory. So thank you very much.
Thanks, Balaji. So we have some momentum for you.
Just for me? Yes, but not for the other speakers? Thank you so much.
So the last talk in this session will be given by Professor Asmita Mukherjee. She is currently a professor in the Department of Physics in IIT Bombay. She completed her PhD in Saha Institute of Nuclear Physics. She has also had associations with University of Darmstadt, University of Leiden, Regensburg University, and her interests are in QCD and spin physics. She will talk to us on Nucleon tomography in J, Psi, production and future electron colliders.
Good morning. It's an honor and a pleasure to be here on the occasion of 60th year of IMSc. So first time when I visited Mat Science was, I think, 1998 in a school organized by Rahul Basu for PhD students. So I was a PhD student at that time. So that was my first visit here. And since then I have visited here many times. Each visit was very pleasant as well as fruitful. In the later years I have been interacting with Ravindran and his group on interesting topics. And I look forward to many such fruitful visits in the future. So today I will be talking about Nucleon tomography in Jepchai production at the future electron-ion collider. So this is about the structure of nucleons which build the matter. In terms of quarks and gluons, this structure is still not understood it is still not understood, let's say, completely. So as we all know, matter is built by atoms. So at the, so if you look at matter, let's say in a length scale of 10 to the power minus 10 meters, you will see some atoms. At the center of the atoms, there's a nucleus, and then electrons orbit around it. But this is not the fundamental particles. The atoms are not fundamental particles, neither is the nucleus. So if you can see, if you can look into the nucleus at a length scale, let's say 10 to the power minus 14 meters, you will see substructures in it. So nucleus is built from various two types of other particles. These are called protons or neutrons, or collectively nucleons. Then if you probe further, let's say at 10 to the power minus 15 meters, you will see these protons and neutrons are also not fundamental point particles. They are built from even more tinier objects. These are called quarks. So the size of these quarks would be even less than 10 to the power minus 19 meters. So how would you really see such tiny, tiny objects? You don't see these tiny, tiny objects by really placing the matter under a very powerful microscope. When I am saying that it is 10 to the power minus 19 meters, it is a measure of the energy with which you have to probe matter. So we see these tiny structures by bombarding two beams of atoms or two beams of nucleons at high energy. I am going to discuss that soon. So various interesting questions come up in this case. One is that how are these quarks spread inside these nucleons? Do they interact with each other? Yes, now we know they interact with each other by exchange of particles called gluons. Then we know these nucleons, protons or neutrons, they have spin half. So how is this spin half of proton built from the spin and orbital angular momentum of these quarks and also gluons? If you somehow are able to see these protons or nucleons under a very powerful microscope, okay, so how will you see the spatial distribution of these quarks inside it? Is there some correlation between the spins of these quarks? Quarks are also spin half particles that we know. So is there some correlation between the spin and the transverse momentum of these quarks? So these are questions that we are trying to understand even now. So in order to see how really we want to probe or we want to find answers to such questions, let me tell you a bit more about these quarks and gluons. So as I said, we now know that the quarks interact with each other via exchange of gluons, and this coupling is denoted by alpha S. So quark-gluon interaction is called color gauge interaction or QCD, full form is quantum chromodynamics. It is also sometimes called strong interaction. This is one of the four fundamental interactions in nature. So why is it called strong interaction? So you can compare the lifetime of two particles. One decays by its strong interaction. So lifetime of particle decaying by strong interaction would be 10 to the power minus 23 seconds. Whereas lifetime of a particle decaying by electromagnetic interaction would be about 10 to the power minus 20 to 10 to the power minus 16 seconds. One thing is that this coupling alpha S is not constant. That is not a surprise because we know that QED coupling alpha is also not a constant. It changes with energy. So alpha S, the strong coupling, also changes with energy. This kind of change is called running of the coupling. But the striking point in QCD or strong interaction is that this running is completely different from the running in alpha, the QED coupling. The cause of this difference is that gluons interact with each other. Gluons carry colored charge, unlike photons in QED which do not carry electric charge. Photons do not interact with each other, but gluons interact with each other. As a result, we get diagrams in QCD not only like these where gluons form QQ bar loops, but also gluons form gluon loops. Okay? So due to this, the color charge is screened both by virtual quarks and virtual gluons. So let us see these two graphs which shows the striking difference of the QED case as well as the QCD case. On the left hand side, I have shown the plot of alpha versus distance. So distance is inversely proportional to energy. So at large distance or at low energy, alpha is small, whereas at small distance or high energy, alpha is large. Okay? Whereas for the strong coupling alpha S, at large distance alpha S is large, and at small distance or high energy alpha S is small. So these cloud of virtual gluons carry color charge, and as a result the effective color charge decreases. This is the reason why we have this strikingly different behavior of alpha S. So at low energy alpha s is large, that means one cannot use perturbation theory, because in these kind of high energy calculations one uses perturbation theory to calculate various things. So at smaller energies one cannot use perturbation theory, and quarks and gluons, they confine themselves to form hadrons. You cannot see free quarks and gluons. You will always see hadrons or nucleons, so nucleons are a kind of hadrons. Whereas at high energies alpha s is small, and then one can use perturbation theory. In fact, at high energy, when you probe the particles at very, very high energy, you go inside the nucleon, there you can treat the quarks as almost free. Okay? So this is the striking difference between QED and QCD. So as I briefly mentioned, you don't see the matter by putting it under a very powerful microscope. When I say you see the substructure of the matter, means you put the matter, you bombard matters with each other, highly energetic beams of particles, and these particles break up, and from that process you try to see the substructure of these particles. How? That is the object of this talk. So let us consider highly energetic bombardment of electron and proton. Okay. So these kind of, so the electron gets bombarded with the proton and gets scattered, it gets deflected at a certain angle. So at very, very high energy this breaks up the proton. So this is then called deeply inelastic scattering. The proton breaks up into its fundamental constituents, various quarks, and these quarks then again combine together and form different hadrons. So what happens at such a high energy is that there is a photon, sort of a photon coming from the electron that interacts with the quarks inside the nucleon. But this is not a real photon in the sense that this photon has a mass. So in particle physics we call such photons virtual photons. It has a virtuality. The virtuality or the mass of the photon comes from the energy and momentum transferred in this process. Okay. So at very high level of virtuality, this photon interacts with the quarks and forms this final state. Okay, so in this field, energy is usually expressed in units of giga electron volts, where 1 giga electron volt is 1.609 into 10 to the power minus 10 joules. The kind of interaction that I am talking of takes place when the virtuality is of the order of a few 100 giga electron volts. Okay. So in this case, the probability of this lepton-proton interaction, which is also called the cross section, can be given as a product of two parts. One part Q of x gives the probability of finding a quark. So quarks, gluons, antiquarks are sometimes collectively called partons. So Q of x is the probability of finding a parton inside the nucleon with a definite momentum fraction x, and then the photon interacts with it. And then the other part is basically the cross section or probability of this electron quark interaction. So this cross section for the electron quark interaction can be calculated using perturbation theory. This is called the hard part of the interaction. Whereas the probability of finding a quark inside the nucleon carrying a definite momentum fraction cannot be calculated perturbatively. This is called parton distribution function or collinear parton distribution. So more about this collinear parton distribution. So what you are doing here is that you are bombarding highly energetic, let us say electron with proton. So there will be Lorentz contraction. So in the direction of motion there will be Lorentz contraction, so proton will not be spherical anymore. It will be like a pancake in the transverse plane. And these quarks are scattered on this transverse plane. So at high energy I can treat these quarks as free. So that is initially what was done. So and also what you can do is that you can neglect the transverse motion of these quarks in this transverse plane, because it is such a highly energetic and it is moving very fast, let us say along the z direction. So these quarks are frozen in the transverse plane, and each of these quarks carry some different fractions x1, x2, x3 or so on of the total momentum of the proton. And that probability of picking up this particular quark with a definite momentum fraction x gives you the collinear parton distribution. It basically gives a one-dimensional description of this proton in terms of the quark. And these quantities parton distributions, as I said, are non-perturbative, and people extract it by fitting experimental data. Later we have seen that, later experiments have shown that these parton distributions not only depend on the momentum fraction x, but they also change with energy scale. They depend on the energy at which the proton is probed, that is the virtuality of the photon. So this is called the scale evolution of the parton distributions, variation of parton distributions with the energy scale. One advantage of this parton distribution or collinear parton distribution is that these are independent of the process. Once it is extracted by fitting data in one process, it can be used to predict cross section in another process as the scale evolution is known. Okay, that gives the predictive power of this kind of field. However, these collinear parton distributions that give sort of one-dimensional picture of the proton is not often enough. Sometimes in experiments, you can try to see the polarization effects of your beams. Okay, we know how to prepare polarized beams and people are actually doing it in experiments. Suppose you prepare a proton beam which is polarized in a plane transverse to the direction of motion. These are transversely polarized proton beams. Then what has been seen since many years, this is a plot from 1991 Fermilab experiment. The cross section of such some processes depend on whether the polarization of the proton is up or down in the transverse plane. These two cross sections are not the same. Okay? So what is the reason? Why normally you would expect that the cross section would be the same because of rotational invariance or something, but they are not the same. So this gives rise to an asymmetry. The asymmetry is defined as the difference of these cross sections up and down divided by the unpolarized cross section. These are called single spin asymmetries. Only one of the beams is polarized. And these large asymmetries have been observed in experiments since many years. And it's large because it's about 30 to 40%. And these large asymmetries cannot be explained in terms of collinear parton distributions. So lots of theoretical studies had been done in this field in the past few decades, and it has been shown that in order to explain this kind of single spin asymmetries, one cannot neglect the transverse motion of these partons. Okay, you cannot really imagine that the partons are frozen in this on this pancake. They are actually moving on this pancake, and you have to take into account the effect of this transverse motion of these partons. So thus comes the concept of TMDs or transverse momentum dependent parton distributions. So these gives the distribution of quarks or gluons or partons inside the proton, both in terms of the longitudinal momentum fraction x and transverse momentum kappa. Okay. And as we are going to see, there are different kinds of TMDs. There are several TMDs, each of these TMDs. So TMDs is the short form of transverse momentum dependent parton distributions, and they play a crucial role in the single spin asymmetries and in some of the azimuthal asymmetries, and different TMDs give a different physics insight into various questions that I listed on the first slide. So these kind of questions are being tried. We are trying to understand these kind of questions in different high energy collider experiments around the globe. So here I give list 4 of them. One is the Large Hadron Collider or LHC, which is located in CERN, Geneva, Switzerland. This bombards highly energetic proton beams or also heavy ion beams with each other. Then this is a picture of the relativistic heavy ion collider, which is located at Brookhaven National Lab, Long Island, US. This also collides highly energetic proton beams or heavy ion beams. This is a picture of a fixed target experiment. Here we have one target that is fixed, and it is bombarded by a highly energetic electron beam. This is the CIBA facility at Jefferson Lab, Virginia, US. And this is a picture of Hera, Daisy Hera, which is located in Germany, Hamburg. So this completed its data taking in 2007. This was also an electron-proton collider. There is one more important collider coming up also in the US. This will bombard highly energetic electron beam with proton and heavy ion beams. This is the Future Electron Ion Collider. So people interested in this field are currently looking forward to the start of operation of this collider. So I am representing the international scientific community in the steering committee of the users group of this collider. And we look forward to a very strong Indian participation, both in theory as well as in experiment. At present, 30 institutes from India are participating, are shown interest in the working of this upcoming collider. So this will be built at the Brookhaven National Lab, and this will collide highly energetic electron beam with proton or heavy ion, and it will basically take snapshots of the proton. So that is what is called tomography. By tomography I mean that we will take two-dimensional many images of this internal structure of this proton, and from there we will get the three-dimensional picture of the proton. In particular, it will try to understand the glue that binds us all, those are the gluons. So these quarks interact by gluon, and so we will try to understand particularly the gluons, and also we will try to understand how the spin half of the proton is made from the spin, and what is the spin of the quarks, and what is the role of the orbital angular momentum of the quarks and gluons. Also, it will explore the correlations between spin and orbital angular momentum as well as the intrinsic transverse momentum. So, the object of this talk is to briefly discuss how it will do so in the context of one particular process. It will not probe only this process, it will do many other things, but I myself am interested in this particular process, and that is why I will give you a little bit more details on how this collider will probe the questions that I raised in this process. So, let us consider a bit the theory of a process where we are observing a particular hadron in the final state in electron-proton collision. Okay. So, we are bombarding highly energetic electron beam with proton beam, that is what that will be done at the electron ion collider, and in the final state we are observing this scattered electron. Not only that, we are observing some particular hadron, let us say Jepchai or something else, with a certain transverse momentum. We place the detector and we also observe this hadron. These kind of processes are called semi-inclusive deep inelastic scattering. So, these TMDs play a very crucial role in some of the observables in this kind of semi-inclusive deep inelastic scattering, particularly the single spin asymmetries and asymmetries in the azimuthal angular distribution of this final hadron. Okay. So, the cross section for these kind of processes can be written in terms of two parts as a product or convolution of two parts. As I said, one of these parts is the interaction of the electron with the quarks inside the nucleon. This is the perturbative part or the hard scattering part. Then there are these PDFs, parton distributions, which now are the transverse momentum dependent parton distribution. These will play a role here. And there are somewhat similar things in the final state because we are observing not the quarks but the final hadrons. So, we also have to consider the probability that the quarks will combine with each other and form some hadrons. So, these are the fragmentation functions. So, these transverse momentum dependent parton distribution as well as fragmentation functions cannot be calculated in perturbation theory. Okay. Only this part, the hard part, can be calculated order by order in perturbation theory. Each of these parts depend on the scale of the interaction, and the scale dependence becomes smaller and smaller. So, scale dependence gives you a theoretical uncertainty, and this can be reduced further and further by going to higher and higher order in this perturbation theory. Okay. So, this is called generalized factorization, and this is really remarkable that at high energy these kind of cross sections can be factored into these parts. This gives the predictive power. Although I must say that this generalized factorization including intrinsic transverse momentum is not proven for all processes. One complication comes in here, as I said before, the predictive power comes because the collinear parton distributions which we are familiar with, they are independent of the process. So, if we extract the collinear parton distribution in one process, then we can use the same parton distribution to predict the cross section in another process. The problem here is that when you incorporate the transverse momentum, that is not so. The TMD PDFs depend on the process. These process dependence of TMD PDF comes from the initial and final state interaction or the gauge link or Wilson line. So, before I briefly discuss that, let me tell you what are the different TMD PDFs. As I said, there are several TMD PDFs. Each of these PDFs give different insights into the quark-gluon picture of the proton. So, there are 8 TMD PDFs at leading twist or at leading level of 1 by q square for quarks. Okay. So, these 3, so for example, this F1, if we look for unpolarized quark inside unpolarized proton, then we have F1. If we look for longitudinally polarized quark inside a longitudinally polarized proton, we will have G1. If we look for transversely polarized quark in a transversely polarized proton, we will have H1. Okay, so these 3 TMD PDFs are non-zero even if you integrate over transverse momentum, but not the others. Okay. Then several TMD PDFs have different properties, like some of them are odd under time reversal transformation, some of them are even under time reversal transformation. And there are different physics interpretation of all these TMDs. So in this talk, we will be talking about the Sievert's function TMD PDF, which is one of the 2 time reversal odd TMD PDFs. Okay. And the advantage is that each of these TMD PDFs not only gives different physics, but they contribute in experiment, they contribute in different manner. That is, they contribute in different azimuthal asymmetries in an experiment. That is why we can separate them. So to illustrate this different contribution, I will just show you, this is one of the few technical slides. I will show you the expression. If you calculate this cross section for this lepton-proton interaction, the semi-inclusive diploistic scattering, it will look like this. Here we have considered a transversely polarized proton. The proton is transversely polarized, and you calculate the cross section, which is differential in the transverse momentum of the outgoing hadron as well as the transverse spin. This will have different kind of azimuthal modulations. You see all these cos phi h is the azimuthal angle of the hadron you are observing, and then phi s is the azimuthal angle of the spin, transverse spin of the proton. There are different kinds of azimuthal modulations. And each of these azimuthal modulation term will come with a different coefficient. This, for example, comes with FUU cos phi, this is FUU cos 2 phi and so on. And these kind of coefficients will carry these TMD parton distribution and TMD fragmentation function. For example, since we are talking about Sievert's function TMD, this Sievert's function TMD will sit only in one particular azimuthal modulation. This is the sin phi h minus phi s term. Phi h is the same as phi. So if from this measurement one can somehow extract this sin phi h minus phi s modulation, we can get information on this Sievert's function, if we know the fragmentation function, which is known by the way. Similarly, by extracting the cos 2 phi h modulation from the data, we can get information of some other TMD. Okay? That is what people are doing actually in these experiments, and theorists are also trying to gain insights into these questions by calculating these coefficients using models or parameterizations. I am a theorist, so that is what I am trying to do. Okay, so let me tell you a bit more on this particular TMD Sievert's function. What is Sievert's function? So Sievert's function TMD was first proposed by Dennis Sieverts in 1990. It is related to the probability to find an unpolarized quark inside a transversely polarized proton. Okay. In fact, there are many theoretical works in recent days. It has been found that it includes the correlation between the quark intrinsic transverse momentum and the transverse spin of the proton. That is the physics insight that it gives. In fact, in some model calculations, it has been shown to be related to the orbital angular momentum of the quarks inside the nucleon. Okay, so these quarks are not stationary, they are moving. So there should be some orbital angular momentum of the quarks as well as the gluons. So quark Sievert's function in some models is related to the orbital angular momentum of the quarks. One interesting thing is that it is odd under time reversal transformation. But when you observe some effect of this, it must be time reversal even. So what happens is that it combines with another time reversal odd effect to give an observable asymmetry. And actually this was a matter of very strong debate in this field about 20 years back. In fact, Collins wrote a paper showing that the Sievert's function should be 0 because it comes from time reversal odd effect. But then Brodsky, Huang and Smith did a seminal calculation in a model and showed how it can be non-zero and how an observable effect can come. So this is the famous paper of Brodsky, Huang and Smith. So they did a simple calculation, not in QCD, but in some simple model which is also known as scalar diquark model. And they showed that Sievert's function can be non-zero, and the required other time reversal odd part is basically a phase factor which comes from the final state interaction and it depends on proton spin polarization. So you have a process like this, so electron and proton scattering, it goes through this virtual photon. So this virtual photon interacts with one quark inside the nucleon, which is also called the active quark. Active quark is the one that participates in the interaction. But proton does not have one quark, it has many other quarks and gluons. These other quarks and gluons are collectively called spectators. They are not actively participating in the interaction, they are spectators. But these quark, the active quark, can have some interaction with these spectators via some exchange of gluons. So these in this process are the final state interaction. This is just a very simple diagram. There are there can be many gluon exchanges here. Okay? And this final state interaction here gives a very important phase that gives rise to non-zero Sieverts asymmetry. Okay? So after that, people have done extensive calculations in gauge theory, lambda QCD, and they have shown that this is actually related to the gauge link or Wilson 9 contribution that is required for gauge invariance. So this has been a very active field in the past 20 years, or let's say 10 years. So as I said before, Sieverts function or TMDs, in particular the TMDs that are odd under time reversal, they are process dependent. They depend on the process in which they are probed. Let us consider two different kinds of process. One is the semi-inclusive deep inelastic scattering, that is what I have been discussing so far. There is another process which is called Rayleigh process, where you bombard two proton beams and in the final state you observe a lepton pair, okay, like electron, positron or so on. So this is called a Rayleigh process. And this gauge link or this kind of gluon exchange depends on specific process. In some process it can be a final state interaction like semi-inclusive deep inelastic scattering. In some process like Rayleigh, it can be an initial state interaction. And the gauge link structure in these two processes are different. So this gives a very powerful prediction, theoretical prediction. Gauge link structure or Sieverts function in Rayleigh process is same in magnitude but opposite in sign compared to the Sieverts function probed in semi-inclusive deep inelastic scattering, because of the particular nature of the gauge link in these two different processes. Among other things, this is one of the very interesting questions that we still need to understand experimentally. Initial results from the relativistic heavy ion collider indeed favors this kind of sign change, but more data is required here. So here the electron ion collider, future electron ion collider will play a very important role. Okay, let us come to the gluon Sieverts function. So far I was showing you quark TMDs, but there are also gluon TMDs. Okay? So there are both quarks, antiquarks and gluons inside the nucleon. So like quarks, one can also think of some gluon mediated interactions, okay? And then we have to talk about gluon TMDs. Gluon Sieverts function is much less understood than quark Sieverts function. In fact, the process dependence of gluon Sieverts function is more involved, as gluon TMDs, I skip all the details, but gluon TMDs involves two gauge links or Wilson line compared to quark TMDs that have only one Wilson line. So here we discuss a process that probe the gluon Sieverts function at the EIC or electron ion collider, which is Jebshai production in the EP collision, where we have a transversely polarized proton. In fact, there are some recent results from another experiment called COMPASS at CERN on gluon Sieverts function. It actually shows effect of non-zero gluon Sieverts function. So gluon Sieverts function is important and it plays a role, a very important role for some processes. Now let us come to Jebshai. What is a Jebshai? So Jebshai is a particle. It is a bound state of one charm and anti-charm quark. Okay, these are heavy quarks. So it has mass 3.09 GeV by c square. It was discovered in 1974 by two experiments, one at SLAC, Stanford, and the other at Brookhaven. The production mechanism of this Jebshai particle, it is a bound state of these heavy quarks, it is a meson. Production mechanism is still not very well established. There are mainly three models or mechanisms in the market. One is called color evaporation model, one is called color singlet model, and the most widely used is based on non-relativistic QCD. And here one assumes a factorized form of the cross section, that is initial state quark or gluons forms a heavy quark pair, C bar pair, perturbatively, that is a hard process. And this C bar pair then emits some soft gluons that is a non-perturbative process, and they form the bound state of the Jepchai particle. So this non-perturbative process is included in a non-perturbative matrix element, and this is called the long distance matrix elements or LDMEs. So these LDMEs are the non-perturbative part that can be extracted by data from various experiments, and the other part, that is where the quark or gluons forms the C bar pair, that is the hard part that people calculate in perturbation theory. Okay. And this heavy quark pair can be formed both in color singlet or in color octet states. So let us consider this particular process. Electron and transversely polarized proton, they bombard, and in the final state we are observing the scattered electron as well as a Jepchai particle. So I was talking about this semi-inclusive deep inelastic scattering with one observed hadron. Here my observed hadron is this Jepchai particle. So if you want to calculate this kind of cross section theoretically, at leading order you will get contribution from these two Feynman diagrams. These are the virtual photon interacting with gluon in the proton and giving rise to a C bar pair. These are the heavy quark pairs in the final state, and this C and C bar then later forms Jepchai through a non-perturbative process or LDMEs. So the amplitude can be written in this way, where this O mu nu comes from these Feynman diagrams, that is the hard or perturbative part. PSSSZ is the spin projection operator that projects out spin triplet or spin singlet, and these are related to the non-perturbative part or the LDMEs.
So, a couple of more minutes. So,
Yeah, sure. Okay, so from the diagram you can get the hard part that will look like this, and the theoretical estimates are arranged in double expansion in terms of a velocity parameter v. So NRQCD means that we associate a velocity parameter v which is assumed to be small with this process. So the theoretical predictions are arranged in a double expansion in terms of a velocity parameter v as well as the coupling alpha s. And these LDMEs, long distance matrix elements, they have different scaling behavior with respect to the velocity parameter v. Okay. In fact, here for our relevance only the color octet formation is important, because as was shown in this paper, single spin asymmetry can be non-zero in EP collision if the heavy quark pair is formed in the color octet state. So as I do not have much time, let me skip all these things. So these are a few details of calculations of this cross section or the asymmetry. So here we are interested in calculating the particular azimuthal modulation that contains the Sievert's function. So what basically we do is that we calculate the numerator and denominator of this particular azimuthal modulation, and when we integrate over phi, all the other azimuthal modulations go away. And so in that case we extract the contribution of only the Sievert's function theoretically. That is the aim. And the coefficients of this Sievert's function comes from these diagrams as well as the LDMEs. As I said before, several LDMEs will contribute to this single observable, as the C bar pair can be produced in various states, and then it emits the soft gluon and becomes a Jepchai. So let me skip this also. Okay. Also, to make a theoretical estimate of the Sievert's asymmetry, one has to make some models or parameterizations of the TMDs. The TMDs are not known, that is what we are trying to probe in this experiment. However, for theoretical predictions we have to take help of some model or parameterizations. So there are several models of parameterizations of the Sievert's function TMDs. In most models, the intrinsic transverse momentum dependence of these quarks or gluons are taken as a Gaussian. Okay. So we use one particular parameterization that looks like this. The parameters of these models are obtained by fitting data, and the scale evolution or evolution of the TMDs with the energy scale is also known, that is different from the collinear parton distributions. So here I show some representative plot of this Sievert's asymmetry. This work was done in collaboration with my then student Rajesh. The asymmetry is negative, but you see, so different plots correspond to the different model or different parameterization of the gluon Sievert's function. What you see here is that there is a heavy dependence of the asymmetry, the magnitude as well as the sign on this parameterization or model dependence of this TMD Sievert's function. This is why we need more data for this process from the future electron ion collider that will fix these discrepancies, okay, that will fix the model to a large extent. In fact, the existing data from the COMPASS collaboration has only 2 data points on this asymmetry with huge error bars. So here we plot these data points together with our prediction. Our prediction at leading order is only at z equal to 1. You see one such model falls within the error bar, but these results are not that conclusive. Not only this process, there are several other processes even including Jepchai production that can probe the gluon-Sievers function. Another process is inclusive production, photo production of Jepchai. Here the interaction goes through via a almost real photon, that is virtuality of the photon is very small. This involves contribution from higher level Feynman diagrams. So as you go to higher and higher levels, you get more and more diagrams. So contributions from all these things have to be incorporated, and you can calculate the asymmetry. This is from another reference together with my students Rajesh and Raj. And here again you see the effect of the different models of gluon TMD. It also depends whether you have a positive asymmetry or a negative asymmetry on the model. Okay. So these objects need better data in order to pinpoint whether what is exactly the parameterization of the gluon-Sievers function. One more process, okay, so here we have shown the plot of the cross section, not the asymmetry but the cross section for unpolarized process. The advantage is that for this process the data from the past collider Hera actually exists, and you can compare with those data, and you see that there is practically very good agreement with the Hera data provided you include both the color singlet and color octet contributions of the heavy quark pair. And for example, one can also consider a back-to-back production of Jepchai and gluon jet that will also give have sensitivity to gluon-Sievers function. This is the plot of the asymmetry in this particular process, and you see significantly large asymmetry. Contribution from quarks is very small. So this is another golden channel which will probe the gluon-Sievers function at the future electron ion collider. This brings me to my summary. The upcoming electron ion collider at BNL will give new insight into the fundamental building blocks of matter, in particular to the gluons that binds us all. It will probe the TMDs over a wide kinematical region and with high luminosity. What we discussed here is that theoretical predictions of some of the observables in heavy quarkonium production that can probe one of the particular TMD that is of interest, which is the gluon-Sievers function. This TMD gives a correlation between the intrinsic transverse motion of the gluons with the transverse spin of the proton, and it also is related or thought to be related to the orbital angular momentum of the gluons. Now when we talk of gluon-Sievers function, this can probe the orbital angular momentum of the gluons. And single spin and azimuthal asymmetries can give insight into this. Okay, so thus we can hope to get some Nucleon tomography in terms of gluons. I would like to end my talk with this picture, but before I came here I saw the same picture just outside this room. This is a picture from 2008 WEP that was organized here in IMSc. The convener was Rahul Basu, who is here, and quite a few of us can identify ourselves in this picture. And I could not find a picture of the 2000 WEP, by the way, and I saw that there are no pictures outside also. Thank you.
Thanks, Asmit. So we have a small memento for you. Yeah, so thanks all of you. This concludes this session. So are there any announcement from the organizers? Yeah, we'll meet in 15 minutes. The coffee will be served outside, I believe.
Mic check.
Everybody? Good morning, everybody. As part of the 60-year celebrations of IMSc, we are extremely delighted to have a panel discussion on this day, the 3rd January, which also happens to be the foundation day of the Institute of Mathematical Sciences. Today, we have a distinguished panel of eminent scientists, institution builders, and policy makers. I'm very happy to introduce the panelists to you. We have Professor V. Ravindran, Director of the Institute of Mathematical Sciences, Professor Rajiva L. Karandikar, former Director of the Chennai Mathematical Institute and currently the Chairperson of the National Statistical Commission. We are also joined by Professor Madhavan Mukund, Director of the Chennai Mathematical Institute and National Coordinator of the Indian Computing Olympiad. We have Dr. Soumya Swaminathan, former Chief Scientist, World Health Organization, former Director General of ICMR, and former Director of National Institute for Research in Tuberculosis, which is situated in Chennai. We have Dr. G.N. Hariharan, Executive Director, MS Swaminathan Research Foundation, Dr. B. Venkatraman, Indira Gandhi Center for Atomic Research Director, and Dr. Smita Srivastava, Professor, Department of Biotechnology at IIT Madras and Faculty in charge of the Bio Incubator at the IIT Madras Research Park. It is very unfortunate that Professor V. Kamakoti, Director of IIT Madras, could not join us today. I, C. Ramya, and Professor S. Vishwanath are happy to moderate this panel discussion. The topic for today's panel discussion is Chennai as a science hub. I'll sit down. Okay, so given that the topic for today's discussion is Chennai as a science hub, Chennai has several premier research labs and institutions that conduct research in fundamental as well as applied sciences in various scientific disciplines. So we would like to hear your thoughts on the strengths and weaknesses of the existing scientific ecosystem in Chennai.
So there are lots of mics, I think. So it'll be nice if each of our panelists could just make an opening statement, just your thoughts on what you see as the strengths and weaknesses of.
So thank you for inviting me here. I think it's a privilege to be here among all the experienced ones. My thought on the Chennai as a science hub, the strength is in the fact that there are many national level, international level institutes of eminence, so-called at Chennai. And the bottleneck could be, there is a lot to be leveraged, and there seems to be a gap, still a scope I should mention to give a positive connotation to it, for more interactions among these institutes for greater good of the society and also in terms of translational component. Thank you.
Thanks. So I think, yeah, the strengths have been the large number of institutions, as was mentioned, IIT, IMSc, so many, even Madras University has a glorious tradition of science, and newer institutions like CMI. So I think, but there is a clear bias, I think, in terms of areas. I think it's very much more heavy in terms of the mathematical sciences and engineering. So I think that Smita's life sciences, I think, deserve a much larger role. So that would be, I think, one aspect which probably should be addressed somehow. The other thing I think is that though we have a large number of research level institutions working in science, I think relatively speaking there are not that many teaching opportunities or studying opportunities for students wanting to enter science at an undergraduate level in Chennai. So I think you have to, I mean, we don't have the equivalent of ICERs and such institutions here where students can aspire to learn science at the highest level. And so I think that is something maybe which will help, because I think that's where I think we're losing the plot. So at CMI, we don't get students from Chennai for mathematics, but I think this would also be the case in other sciences. And I think if we don't have an opportunity to showcase this at a local level, it deters students, I think, from joining these streams.
This particular city is very lucky because, as everyone knows, that there are plenty of, engineering colleges, whether it's IIT, Anna University, two institutes like IMSc and CMI, and a lot of small colleges actually. And if you're talking about science, there is a big gap between, these elite institutions and then small colleges actually where the real science is, supposed to be taught. Okay, also schools. Okay, there's a big gap between these two actually. People from colleges, small colleges, they think there is some kind of science that is done here that we cannot understand, and then scientists from this elite institute think that these are places that it is not very important that we should go and actually spend time. So this gap is what I think is very big in Chennai, that whichever universities, colleges I visited actually. So this is something that in my opinion, while we have rich institutions, this gap is what is actually making me very much bothering actually. So I think that's something that I wanted to actually point out.
Yeah. Hello. I agree with the views of all the three of them, and in particular this gap. Generally, it is there across the country, but in Chennai, it seems really too much. As Madhavan mentioned, the number of students from Chennai who want to join CMI, forget whether admitted, itself is extremely small. So I know IMSc has been doing a lot of outreach activities. I think we should, all the institutions should do them collectively and in a much wider way, and also connect with the teaching faculty across the colleges so that the level there goes up and some kind of connectivity is built. So the other thing is about as a science hub, somehow nationwide, when they talk about, they think about South means only Bangalore. They don't talk about Chennai. So we need to create that awareness. How to do that is a different question, but that is the other aspect. It is very good, but it doesn't come up in anybody's talk when they talk about South and science. So that's the other thing we should do.
I think very good points have been made already. Obviously, there are a number of very good institutions, especially even if you just take South Chennai or just even the Taramani area, you will have more than half a dozen institutions that are each doing exemplary work. I know we don't have today probably some of the health or the medical research related, but we have several of those as well. So I would say that in addition to the points already mentioned about, firstly, Chennai not being known as a science hub, which is unfortunate in spite of all the work that goes on in the different institutions. Secondly, I think the disconnect with the public. I feel that for the future, I think one of the most important things is going to be the science literacy of people, and this has to start from school children. Not just an interest in science or wanting to study science, that's very important. We need many more good students going into science, but also just an understanding of scientific principles, which everybody needs to have, regardless of whether they later on do liberal arts or journalism or anything. I think the pandemic showed us how misinformed people can really have very harmful impacts on society. And I think today when I speak with young people, I don't see that they have that critical thinking which is needed, I think, for every individual. So I would think that the science institutions together can have a big impact on that if we decide to do something working with school children. The third area I would argue, but we're not having an impact on, is government policy. And I think we, between us, have so much data. The National Statistics Commission obviously puts out a lot of information. There's loads of data out there. Between us collectively, I'm sure we have a lot. But how effectively are we using this to inform government policy making? And today, I think that if you look at Chennai, I think we're heading for, in terms of climate change, huge impacts on all of us. Heat, as well as sea level rise, as well as on our food systems, etc. And so I think collectively we can also do a lot to work with government to bring the data and evidence that we have to have some impact on how the policies are being shaped for the future. And Tamil Nadu is a relatively progressive state, and so we should be able to move the needle, I think, much more.
Yeah, thank you IMSc for this wonderful opportunity. You know, coming almost sixth in the speaker line, it will be difficult to catch, but the seeds for the Science City, or Chennai as a science hub, was sown in 1993 when the then Chief Minister Jayalalitha inaugurated the MS Swaminathan Research Foundation. The idea, in fact, C. Subramaniam seeded this idea to Jayalalitha. He was, Dr. Soumya made that point. The constellation of institutions in the Guindy, Taramani, Adayar region. There are about 69 different institutions available, including MGR Medical University and the King's Research Institute. So at that time itself, immediately in the next year, the Science City was formed. Now you can see the organization within the Birla Planetarium campus. And the first chairperson of the Science City was none other than Professor Swaminathan himself. And later now, today, the Higher Education Minister is the chairperson of the whole thing. And Dr. Soumya also mentioned about the very critical points. See, inculcating scientific temper is the need of the hour. And under the broad canvas of Science City, a lot of networking, although even at that point of time, even they had a MALIBNet 30 years before. MALIBNet was there in the city, and institutions were getting connected and all those things. But slowly we started drifting away from the central theme. Now the need of the hour is inculcating scientific temper, and also each one need to know what the other institutions are doing. Better networking. I was just speaking to the professor from IIT, and next to us is the Samir. They're a giant institution in the area of electromagnetic research. We started conversing, and we understand a lot more they can offer with respect to electromagnetic related research, with respect to agriculture is concerned, especially to map the soil salinity, increasing soil salinity due to climate change, both surface as well as subsurface soil salinity and so on. So a lot of new products, new ideas can only come in only when the interactions happen. And especially from the foundation side, we have a very interesting program called, again, advised by Professor Swaminathan, is the Every Child a Scientist program. This is specifically focusing on the young children studying in the corporation schools where the facilities are not that great. And we bring them in and provide them all kind of infrastructure, necessary infrastructure, both digital and also analog, wherein they are asked, they are made to ask questions, logical thinking, and also ask questions. In that way, we were able to, at least 3,000 students have passed away from our system right now. And the impact levels are very, very, very nice. We even published a paper in CMI about the impact, how exactly it transformed the kid from an ordinary kid to a different level. So these kind of pathways and avenues are available. Then science education, or Chennai as a science hub, will automatically will happen. Another very interesting dimension is 30 years before, we also established, along with the support of Department of Biotechnology, the first Golden Jubilee Biotech Park for women in Siruseri, This is the first ever park exclusively to encourage women to take science as a career. And there are a lot of entrepreneurs received, they were able to set up their own shops, and now wonderful bioproducts are available. And similarly, a lot of students also come in for training, and after that, we also see they get good positions in various institutions as well. Silently, these are all the things happening, but to make it very strong, again, we have to join together and make it happen in the true sense. Thank you.
Thank you. And at the outset, thanks to IMSc for giving this opportunity. I come from the Department of Atomic Energy, which is an applied research organization, Indira Gandhi Center for Atomic Research. So having heard to the galaxy of speakers here, I had the opportunity to tour across Tamil Nadu as part of what you call creating an awareness on basic science as well as the DI technologies. But during the course of interactions in the last 10 years with over about 50,000 students, the fundamental thing that came to the mind was awareness about the scientific principles, the basic scientific principles, and also about the scientific institutions in Tamil Nadu is grossly lacking. Just to give you an example, okay, I was coming from in a flight from Madurai to Chennai. Next to me was a lady. I was just talking to her. She was working in a bank actually, but basically a science graduate from American College, Madurai. I was just asking her whether you know Kalpakam, etc. She said she doesn't know. And incidentally, it so happened that 1 week later, I had a call from the Department of Atomic Energy about an article which appeared in the press. So they said, you please check up with one of the eminent professors in IIT, because he was associated with that press article. I rang up, and the PA who took up the phone, I told her that I'm calling from this particular institution. Can you connect me to your professor? She said, no. Then I had to tell that I'm from Kalpakam. I said, do you know Kalpakam? Then in a typical style, I have heard of Kalavakam, I've heard of Karapakam, but not Kalpakam, just in Chennai. Well, the point here is awareness among us. When we had our education, we were knowing about all the institutions. So once these people are not aware about the scientific institutions, there is no doubt that Chennai is a hub of physical, chemical, and biological sciences and engineering sciences. But if I do not create that sort of awareness, then how do we expect people to take up research or any other thing in science? One. Second thing, what we found was, a lack of awareness on what are the opportunities you would have on taking up a scientific career, be it in research, be it in research organizations, etc. So this is the area where definitely a good amount of networking is required. This is the first part. The second part is, we as institutions, let us do a little bit of self-searching. We have so many institutions in and around Chennai. How many of us interact with each other, know our strengths, know our areas where we can collaborate? After all, science has to go back to society. And that can be done only when we interact among ourselves. There are a lot of areas and opportunities available, but that can open up if we start self-discussion among ourselves. Today, if you talk of healthcare, they talk of artificial intelligence. The role of AI, they say, is going to be a big boon. Of course, it cannot replace a doctor. But still, it can aid. And when I talk of rural health technologies, these are the technologies which are going to aid. And in this particular case, a synergism between the academic and the research institutions would definitely go a long way. So the point to ponder here is, among us, we need to have interactions, and we should know the strength and areas where we can collaborate, take these messages to the students around and create in them the spark. Going back 20 or 30 years down the line, you see that at that time, engineering was not that prominent. We had very good people coming into the science areas also. So that sort of thing needs to be recreated. And ultimately, a good amount of synergism need to be built in among us. And definitely, I think with these, armed with these, if probably we go back, definitely I think many of these things can be addressed. These are some small thoughts.
Thank you. Thank you very much to all the panelists. Okay. So I think the point about synergy, which is sort of being brought out by all the panelists. So I guess everyone, I think, more or less agrees with the sentiment that while we have several institutes, somehow we don't seem to be talking to each other as much as we should be. So I sort of want to harp on that just a little bit more and ask your opinions on this. So, I mean, we just sort of looked up Wikipedia just out of, curiosity, and it lists some 24 or 27 institutions in Chennai, and I'm sure they're missing many more. So on the one hand, there is this research aspect, for example. So research collaborations, Sir mentioned Samin as an example where MSSRF has collaborated with actual tangible benefits. So I just want to know, how do you think these things can be set up, or germinated? I mean, speaking for myself, I can't imagine, I don't even know where my expertise would be useful, right? Or that's usually the case, I think, with most scientists. You're well-meaning, but not necessarily informed of where it can. So there is some, I don't know, some structural framework, some, I don't know. So it's a vague question, but I'd be happy for any thoughts you may have on this.
I can talk about what we are doing as bio-incubator at IIT Madras and what steps IIT Madras is taking for outreach as well as to enhance industry-academia collaborations. Now, what we are doing is we are trying to bridge the gap by having R&D fairs where we invite industry, we invite school, college students to make them aware of what is happening, what kind of research is happening at IIT, to go deeper, recently the Center for Industrial Consultancy and Sponsored Research had held department-wise, domain-specific R&D fairs, which was open for 2 days to the entire students and colleges who were free to visit, to know what goes on, to motivate them to get into research, to motivate, and then there was entire 1 day exclusively meant for industry visits to these department R&D fairs, to organically build that connect between the industry, academia, and also the population at large with IITs. Now, as a bio-incubator, what we attempted, although it could not materialize, but I think we continuously strive to do so, is to be a part of these science and technology clusters. So surprisingly, when we were applying to DBT Urjit call, which was a call for such a kind of collaboration on translational research between industry, academia in this zone, we found that one is missing here. And with such a coastal and marine bioresource available, we attempted where these institute-driven incubators could club with various institutes where we were trying to collaborate with ICAR, SIBA, we were trying to collaborate with the National Institute of Marine Technology, and various other places, in fact, Tanuas also. So I think these can be the ways where you can make platforms, otherwise it's always individually driven. The faculty is interested, they try to scout for the collaborators at various institutes through different connects, and then they approach. So a more proactive way would be to establish science and technology clusters or consortiums, which can be domain specific.
Sorry. No, I think this is a very good idea of having a domain-specific interactions, because let's say there are 30 or 40 institutions and everybody cannot work together on everything. But if we identify some themes or areas where we believe that there is enough expertise available and institutions are working on it, and if taken forward, then those can benefit society more largely. I mean, I was thinking one of the areas really is data, and we don't seem to have a very good way of especially integrating different sources of data. So we have surveys or other kind of regular data collection systems like for climatic or meteorological. At the same time, we also have data on trade, on economy, and we have data on health parameters. And I think with the kind of expertise we have, particularly here at this institute, IIT Madras, I would think of a few other institutions with capacity for big data analysis, storage, and interpretation. And that also then allows many questions to be asked. Of course, it's not a trivial task, I think, to do that. But if a few institutions would start by agreeing on such a system of data, pooling in data, data sharing, wherever there is non-confidential, non-sensitive data that can be shared. And I think government needs to play a role in this because they do have a lot of the data. I was thinking about air pollution, for example, and its impact on health. We see in a lot of public debate on this, particularly in North India in the winter months. It dies down, then again the following year, the same thing starts again. But essentially, we're not really effectively doing anything. And cities like Chennai, the air quality is progressively worsening from the data that I can see. This impacts all of us, you know, wherever we live, or whatever we do. I mean, air quality is something that is silently killing millions of Indians, and none of us are really waking up to the fact. Similarly, you know, there are other things which will have fundamental impacts on us. So I think if we pick a few, I mean, there is, of course, always the area of basic science, of research that needs to go on, but there may be also very concrete things. Road traffic accidents. Is there nothing that we can do collectively to take some action? Best by monitoring the data on road traffic accidents to try to reduce. This has been done actually in other places. Water quality, the quality of, you know, publicly available spaces and things like that. But we need data to show that these things are beneficial for humans. Otherwise, there's sometimes a denial of the fact, or you know, this. You need to convince people by showing the relationship between green spaces, having open spaces, and mental health, for example. So there could be many. Again, I'm talking more from the health point of view, obviously, because that's my domain expertise, but I'm sure in many areas this could. So about data, I'm sure you have a lot of insights on this.
Well, I've just taken over as the chairman, and I'm going to Delhi today, and we are having a first meeting tomorrow. I know there are tons of challenges with data, not just in Tamil Nadu, nationwide. About data is kept in silos and not shared with each other, leave alone with public. But so let's see what we can do there. But coming to your other point, I think health and various other things, or road traffic and so on. I think the institutions could get together and interact at least with the Tamil Nadu government and the local people to create awareness. I mean, just let's say road this thing. We have tried to make efforts and tried to talk to the government. They promise various things that we will get you in, we'll pull you in, but then the thing gets forgotten. So just traffic management. I mean, the accidents are happening because of poor traffic management. If the traffic is managed better, the accidents will come down, and some more training will need to be done. But collectively, we need to talk to the local government or the Tamil Nadu government and involve all of us together. We can't be competing with each other. We have to do it together.
Yeah, the domain-specific issue is one. But at the same time, again, what is emerging is the locale-specific related instantaneous solutions what we can provide to both policymakers as well as to the public. That is where we can play a major role as a group of competent organizations. This is the season where many institutions will start receiving the requests for internship at both postgraduate and the graduate level. Many students approach institutions, and we have very, very, very brilliant, bright students at the same time. Many colleges were also making them to go from one institute to the other and things like that. If we can create a common platform where unfortunate to see young students right from the morning without even taking breakfast, visiting one institution to the other. But at least as a collective, if we can put a platform wherein they can also say, basically the colleges are going to give the bona fide so that the students will approach one institution the other. So at least in a common platform, this is one step closer to bringing the institution with the possible interns together in a common platform, so all institutions will also know. And for that, already the websites are there. The colleges are, somewhere we need to request the colleges to upload their bona fide students' data so that immediately it will reduce the burden of the student to go to one, and ultimately they will end up in labs where, the kind of, the predatory, all those kind of issues are also happening. We are not ready to address them directly, but unfortunately the young minds, even the brilliant minds have to go through this torture and end up in, so internship, we need to, if we can capture them young, and this will also provide us an opportunity, because soon after the internship, he or she will pick up almost the similar research line to continue their professional, research work or what. Yeah.
I found that the idea of one is domain specific. Yes, it has to be domain specific. The second is data part, which is a very valid thing. People are sitting on data, not sharing it also. And even within a state like Tamil Nadu, the possibility, let us take like water quality across the state or the air quality across the state. We can have academic institutions having these sort of problems identified for students who can take it up as a 3-year project or a 5-year project, do a bit of research combining statistics. Then probably this can be taken on, linking up to the health institutions, do epidemiological surveys in those regions. Because there are pockets, we are aware that within the state, there are areas which have a lot of arsenic. There are areas where the air quality is not so good. So what is the effect on the lungs because of that? And the water quality on the renal part or something like that. So if we can do these sort of studies linking up, which is again multi-institutional, here the government can also be connected, because we can rope in the health department also and tell them that, look, these sort of studies are being envisaged and planned. Indicate how you can also support us. We institutions can also put forward a certain thing. So I think that is a very good idea. Probably we can identify areas that are of immediate relevance in especially the healthcare, air quality. Similarly, this is a state where a lot of cyclones also cross. The effect of environment and the subsequently all these sort of things. Today predictions are well there. Very well, good predictions are possible. The impact of that on the society, especially in the coastal areas, inundations, this can also be studied in a broader way. So I think a lot of possibilities exist in these areas.
So given that you have said about data, right? So do we really see that data science is the paradigm that's going to play a major role in the public health sector? We have seen this through the pandemic. And is there some sort of a cross-institutional framework that we can all come up with? Chennai has recently released its first climate change action plan, and the draft is already out. So is there some kind of a cross-institutional framework or umbrella that you could recommend that would help?
Probably this forum can be a starting point.
I'm sure that it can be. It will need a lot more in-depth discussion. So perhaps this panel is serving as a stimulus
Yes.
To set up something like that, or to reinvigorate what Hariharan mentioned, that this has been discussed in the past. There have been attempts made, Science City and so on. Let's reinvigorate that. We should reinvigorate the efforts that were made in the past, on the Science City, to come together again as institutions and focus on these 2 or 3 areas. One is the domain specific, which institutions want to work together on what areas. The second could be around the public involvement and exposure and awareness building on science, and then also the students, how they can be encouraged. The Every Child a Scientist program at the MSSRF is a good model, but is a small, because naturally one institution doing it can only service a certain number of students. I think we have a huge need, even if we just try to cover all the government schools in the city. That itself, I think, would go a long way. And if they get exposure to different kinds of work in different institutions, then I think one of the things when I meet young children who are in class 9, 10, 11, they have no clue at all of their future possibilities. There is no sort of counseling or vocational opportunities, skill development. Even though IIT Madras, for example, has launched so many courses now with the Skill Development Academy, but these kids in corporation schools have no idea. So I think we have to work also with the government departments of education and so on. But if Tamil Nadu really wants a skilled workforce in the future, not just churning out people with degrees without any skills at all, then I think our institutions must work together to support the government to do that. But also to push the government. I think at times, if we work collectively, as you were saying, and not individually, then I think we can have a significant impact.
So especially the things you mentioned about school students, and so for example at Math Science we keep having these programs. I think IIT Madras has it and so on, CMI has it. So every institute somehow does its own thing in isolation, and so I mean for a maybe scientifically interested, I don't know, 8th or 9th standard kid, I suppose between us we probably can offer an experience of several different, looking at various labs, maybe physics, chemistry, health, nutrition, and so on. So how do you have any thoughts on, I mean, I guess it's clear that we should collaborate and so on, but finally the devil is usually in the details of how to actually implement things like this and so on. What do you see are the challenges typically with?
He mentioned about the awareness generation. See, we work in silos, we publish a lot, but our expertise and other things almost get confined to our own campuses only. We are not able to reach out to the larger sections of the society. On one spectrum of the side, you have the policymakers. They are the ones who translate that, when they have to say, such a program is happening here, unless and otherwise they get the necessary, orders from the government or the secretaries to the schools and so on. And if that is not going to happen, then this trend will continue like this. We must reach out in 360 degrees, not just to policymakers, to the schools as well. And at least on an annual basis, if all the institutions can come together and at least have 1 or 2 day kind of a conversation or a symposium kind of a thing, then that will create a platform. There are very many diverse dimensions that are happening, and interfaces are also happening here. We must be able to nurture only when we meet physically. At least now, Dr. Soumya is here, COVID is not attacking us to that great extent. So physical meeting within at least, within Chennai. So we don't need to travel a lot. We need to, have at least annual meeting, we can call that as a science fair or whatever it is. Right now Science Congress is happening in the country. At least within Chennai, we need to have some kind of this kind of a mini Congress or whatever it is. That will create the, cross-learning or cross-talk between the institutions.
I think the major full-time resource. Otherwise, all of us are well-meaning, but then we'll go back to our full-time day jobs, right? So I think if we can, even by rotation, maybe institutions can take on the responsibility of serving as a secretariat. We might have to do some fundraising or something like that to employ 1 or 2 full-time people, because, meetings have to be coordinated, prepare data, notes have to be prepared and those kind of things. So I think it's a really, but I think these kind of practical things are the ones probably that result in us not doing that. There are feeling that we should be doing. And this because other my discussion about what is being done in the Department of Atomic Research
use IMSc for basically. Data science research infrastructure, where they spend about 3 to 4 days going through the various labs, etc. The idea is, once you sensitize them on the possibilities of science and the researches, etc., even if 10% of them come back, it is fruitful. So we thought that we can emulate this, and next year we are planning to have the schools, especially the government schools, in and around Kalpakkam, within a radius of about 30 kilometers. We are able to hold some 25 to 30 schools from there. So have a funding program where they just come inside. We don't talk about atomic energy. Let them go around the science lab. We have the basic physics lab, basic chemistry lab, all these things. Let them go around. We have a farm also, which has been put up by our MS Swaminathan Research on paddy cultivation in Chennai environment. We have atmospheric science also research in that. So go around, create an awareness. Probably this sort of model can be there. This is one. Second thing is, as Madam has indicated, probably we can, once we have indicated, we can liaise with Chennai Science City, and all of the organizations can, we can ask them to organize a program like this, where all the organizations can come together and create this sort of awareness. The mechanism we can always, visibility can be worked with typically. So these can be the starting points. But as you said, yes, there are certain small things which can always be an impediment for the secretary. But one of the institutions can take up this, with of course the permission from that, with very facilities there, and act as a model in that. So this is a good idea. Probably we should not end up, after this we go back, but we should have a concrete action plan which comes out of this particular panel.
I mean, I have a similar experience about, people being not aware of even the institutions actually. There are, I live in a very posh area of Chennai, India. I think I heard that I worked with an institution. We get confused with, even they don't understand this. The CRI is different from IMSc. IMSc is just easier because it is simply because it is just, if you ask them about some, where the CPS is, everybody will say where CPS is actually. It's because it's in the road, or that's what they aspire for actually. I'm not saying it's where they go to CPS. But not knowing that an institution of this kind is really a sense for Chennai students. It's really true. Even my daughter is studying in a reasonably good school. If you ask that friend, that do you know that there is a institute for IMSc? They don't know actually. Okay? They know IIT, they know IMSc, but that's it actually. So I think we are really living in a state of, people are not aware of that there are institutions, there are opportunities. I can share you an instance that actually myself and moved to digital learning school, that's an outreach program. And there were women, girls students actually, they were doing training for I think digital. Okay? Then the question posed by Murthy, so what are you going to do actually? The unanimous answer was that they wanted marriage in second. There was no intention of going upward. Okay? This is really pathetic. That's true even in Chennai. Many of these women students in schools or in colleges, they would like to actually go and settle at home. Okay? It is shameful actually. And we have to tell them actually, there are a lot of opportunities. There are institutions, many institutions in India that you can persuade, you can get salary, you can support your family, you can teach your children. So we are living in that kind of a condition. I think that we had green revolution or white revolution. I think in India, need of the hour is the science, revolution. Because we are only talking about starting a new institution to solve something actually. We don't need a new institution actually. We have enough institutions, but the thing is, we have enough resources actually that we have to tap actually. Like he said, nobody knows about Kalpakam. That's really a shameful thing actually. In Tamil Nadu particularly, because Tamil Nadu we claim that actually we are all, very, in terms of indices and things like that, both laterally, vertically we are, but not knowing. Chennai probably people know, but if you go to Kanyakumari, if you ask them, they may not know anything actually. It's also, it should not be concentrated in one particular place. It should spread, I think, in my opinion, actually, throughout the states, throughout the country, actually. How do you do that, actually? Because, like, we have, everybody knows about what Professor Swaminathan did, Professor Kurian did. Like that, we need some massive movement so that people, at the very early stage, see, we are all only inspired by Ramanujam, Sir C.V. Raman, actually. It should not be just inspiration only. It is also, ground level, people should think that everybody can do science, everybody can do mathematics, everybody can do engineering. There should not be, too much hierarchical in this. I think we have to create an environment of that kind, actually. That awareness is one important. For that, you need resources, actually. You have to train good teachers. How are you going to just change the system by professors of an elite institutions? We cannot do that, actually. We have our own task. Like we have to do our research outwork. We'll have to actually create an environment where the university teachers or college teachers, actually, they do their job. Okay, that means you'll have to have very quality teachers, quality professors. I think that is very important in my opinion, actually. We can contribute, making in terms of giving an idea, but I think resources should be, like reaching out to farmers. Farmers are the resources, actually, that. Like that, the teachers, college teachers, school teachers, we'll have to make them provide, kind of education that the students automatically actually become this. Okay, I think that's a grassroots level we'll have to change. I think it is, we have only one Nobel laureate in physics, such a big country. Okay, we have celebration only for one person. We have to change that actually.
Can I just add one last point on this? I completely concur with the idea that we all in the institutes have our own responsibilities, academic responsibilities, professional responsibilities. Setting up a secretariat would be a good idea. Now, talking about the logistics, maybe every time not only reaching out to the government for funding, I think industry can also be leveraged because there is a good CSR responsibility. So corporate social responsibility can be leveraged to run such a secretariat, and also because dedicated people to run the show is important. So I just wanted to add, maybe more meticulously we need to think on it, but industry can also be involved.
Yeah, adding to that, see, you mentioned we can also contribute. Like the CSR, how the corporate sector is now contributing for the social causes, these scientific institutions also need to have a page or a chapter to really do these kind of activities. I leave it to the larger audience to take a call on that, but within our mandate also, it is our responsibility to communicate what we do to the larger sections of the society. We are communicating, but at a different level, and that too to really stimulate the young minds to take science as a stream of their profession.
So I guess I have a couple of different things to ask from what just was discussed. So one thing I guess I'm hearing is that we need a sort of a unified cross-institutional presence, I suppose, partly to have maybe to be taken a little bit more seriously by government, I suppose, rather than individually talking. And secondly, to sort of collaborate on, say, outreach efforts and so on, maybe with a central secretariat, for example, maybe by rotation, etc. Okay. The CSR thing that you mentioned as well. So, question related to that, typically in say the West, where there are many universities centered in a certain region, clusters as we call them. So typically that's almost always been a seed for a very active, industry, academia. They have all this research triangle park, XYZ park. I guess IITM Research Park is sort of a step in that direction. So somehow Chennai, with all this long history and tradition of science and institutions and so on. So this whole thing of an industry academia partnership, it's slowly taking off, but maybe not in a very big way. So what do you see as the reasons for this? What do you see as the prospects eventually? Is Chennai sort of set to take off big time, or are there structural flaws which prevent it from happening? Is Bangalore to blame? So
here I think, okay, because industry academia interactions, as far as the industries are concerned, they would be having their own set problems. And they know the institutions which have the expertise also. So it would be like a 1:1 basis, the industries would be approaching the institutions. For example, with IIT Chennai, we have a cell which has been going on now for more than 20 years. More than a dozen problems are there which are being worked by the different departments. So that I think it goes on a case-by-case basis. Probably generalization there may be a bit difficult. But okay, I leave it to the members, yes.
So as a faculty in charge of bioincubator here, I can share our efforts into this. So what we have realized that there is a lack of trust between the industry and Indian academia. So how to build that trust organically so as to build in industry-academia collaborations inherently. Now what we try to do is, one is showcase. You keep on inviting the industry to show the R&D projects, to show your capabilities. The second thing was encouraging industries to set up their R&D labs, especially the MSMEs and the SMEs, at educational institutes. Now that becomes a platform for organic interaction. Now this would benefit the industry because they can tap on the talent right at the college level. They can do skill development. The problem statements can be defined as per the need of the industry along with other problem statements. Now where university-driven incubators can play a role is that we try to become a bridge between the industry and academia. Now frankly speaking, as a faculty of IIT Madras as well, now you have so many different research, your own loved research problem statement. So most of us, what we generally as scientists do is, we work one of our favorite problems, which we pick up because of some logic, and then we try to see if that problem can fit the solution in the market, can be a good solution to the problem in the market. Now this is one of the ways to approach it. Another way to approach would be to proactively interact with industry to know their pain points, to define collectively problem statements, and then encourage joint technology developments, to encourage joint IPs, to encourage joint R&D collaborations, whether it is coming as consultancy or whether it is coming as R&D project collaboration or sponsored R&D projects. These in together can lead to more coherent interaction between industry and academia. Now, what we are doing at bioincubator, we are encouraging especially MSMEs and SMEs to establish their R&D labs. Now, this allows them to exploit the ecosystem of IIT Madras. This also helps to develop new IPs, and also we scout for budding entrepreneurs from the system out of these collaborations, if there can be coming out of certain startups in the domain. So I think these are the ways in which we can organically build industry-academia collaborations. And also one more point I wanted to add. The Center for Continuing Education, not only in the research sector for IP creation or product development in the market, we are also working on the educational and skill development aspect, where there has to be a specific body, like what we have as Center for Continuing Education at IIT Madras, which looks into user-oriented programs, apart from routine degree programs which we have, which are also open to industry employees, but they have to go through the entire proper channel of interviews and then selection. But what we do here as user-oriented programs, these are short-term training programs, which are defined in collaboration with industry. Courses can be defined, webinars, these can be online based so that the logistics of stay and can be taken care of. So these are some of the different ways in which we are encouraging industry.
Adding on to that, in fact, the other thing, we always think of research problems or that sort of thing. The industry academic can also be value addition to the educational part of it. So in that way, I was interacting with the director of IIT Hyderabad, Professor B.S. Murthy, who had gone from IIT Chennai. So they have introduced courses for the industrial people, which can be taken at their leisure, but then completed within a time frame where at the end, without much etc., you can get an MTech degree, or at the end get a PhD degree also, which is also very good, because it leads to enhancement of the knowledge, it leads to more interaction. So this is again an area which can be thought of by the other institutions.
Removes the barriers of in situ skill development. So.
Yeah, in the Golden Biotechnology Park for women, we introduced seed fund for young entrepreneurs with the support of BIRAC. It's a competitive proposal-based program, and within 3 months the results will be declared. And many new entrepreneurs submit their applications, and it's really helping them to set up their own shop. Yeah.
So, given that you've said that the startup ecosystem in Chennai is coming up really well, we have had a lot of centers of excellence, right, for dedicated areas. So do you think that in the next decade we will need more and more such centers, or do you think that there should be some unified framework under which we can unite some of these to do impactful research? Each of you had mentioned a different center for different things.
Yeah, I think you need to have some impactful research. Is always a difficult thing to predict. But I think unless you make an investment in doing something long term in some area, you're certainly not going to get it for free. So I think in that sense, I think having some focus on these centers is important, and hopefully it will, I mean, if there is some, as has been discussed, some scope for collaboration and interaction, and it might come out between centers, but I don't think that these are in any way contradictory goals, I think. So I think that, I mean, but whether you should have centers of excellence or whether you should just broadly look for good quality research across a variety of topics is a different issue. But I think if there is a thrust that you want to focus on a specific thing, I mean, biotechnology, some particular aspect, or quantum, or whatever, then maybe it makes sense to assemble people who come, typically in more interdisciplinary things, where you have people with different backgrounds, you might want to assemble them together, which they may not have another forum to meet. See, sometimes this is the problem. You start a new area and they don't fit into one department or another department, then you have to create a framework to bring these people together. So I think that's where these centers really come from, I think, where you have an emerging area which doesn't fit neatly into any existing.
I think, yeah, I fully agree. In that way, probably if you look at the global scenario and look at the way China has grown in the last couple of, years, about a decade back, we should have centers focusing on, with long-term visions like manufacturing technologies. That can be cutting across all the industries, not necessarily a specific industry. And second thing is multidisciplinary engineering sciences, I would say. For example, thinking of a center on imaging science, which can not only look at the industrial problems, but can look at the healthcare problems also, because imaging science is fundamental to biological research also. So that sort of centers are needed, but for which we need to have a little bit of brainstorming with senior people from the industries, from the institutions, and also from the government side.
What we have done is that first question was how can we have whether we can have more number of center of excellence. So I think we should also look into the aspect that there need not be physical center of excellence, there can be virtual center of excellence as well, which become a platform for interaction. Like in terms of startups, what we have done is to benefit our incubated startups with the infrastructure and mentorship available across Tamil Nadu in other incubators. We have developed a consortium of all these incubators, and we hold regular meetings, and this is a virtual kind of a consortium. So where we hold, as Dr. Soumya was mentioning, every time one of the incubators take the leads, and we carry out regular meetings. We then host such combined collaborative programs to the budding entrepreneurs, whether it is in legal aspect, IP aspect, whether it is in technology advancement aspect. So we hold such training programs, these awareness programs to even tier 2 and 3 cities. So I think building up a center of excellence, virtual can be a good idea. And also these virtual consortiums where regular meetings can be held. So I think that will encourage the startups and also leverage the infrastructure and the expertise available at various institutes if it comes to institutes level.
See, I have a different opinion. See, the science and technology is always emerging. We cannot say this is going to be the state of affairs for the next, even for 5 years. So as and when we come across with recent advancement and need, we need to go for these kind of setups, new setups. But at the same time, by linking all of us and see how minimal investment, maximum output kind of a scenario will be better to really make Chennai as a science hub. That will be, we can really save the resources at the same time, deliver the goods in a better way.
Just one more specific question. So, I mean, Chennai is also sort of a medical hub in some sense. I mean, I guess as far as medical care, state-of-the-art medical care is concerned, there is, of course, Dr. Soumya mentioned, data being an area of collaboration, public health versus, say, the scientific institutes. So do you see a greater scope for collaborative sort of medical research in going beyond data and epidemiology and so on? Maybe relating to actual medicine itself, the applications of what our scientific institutes are doing to medicine or to other clinical research, for example. Is that happening to some extent? Is there scope for more contribution from the scientific institutions towards this area?
Yeah, I think definitely a lot of scope. I think in several ways. The first one is to identify and articulate the problem or the gaps, right? So if you look at the area of medicine and affordable healthcare, there are many gaps that we have today. And particularly when we think about diagnosis, diagnosis as such has been neglected in many countries, including in India. Now we realize the importance of diagnostics, and especially during COVID, even genomic surveillance expanded a lot, etc. But basic, simple diagnostics, even today in primary healthcare centers, are not available, let alone self-testing and self-care, which is also taking off in a big way. And for many chronic diseases, you need that accessibility and affordability. Another area where I've been impressed with IIT and innovation there is in the area of affordable assistive devices. Today we have a growing need, as people are aging and living longer, a need for assistive devices, whether it is spectacles or hearing aids or walking sticks, or Sujata has made these wheelchairs which can actually help you to stand up. Most people, especially those who can't afford these things today, are still managing without, and therefore the quality of life is not good. And in India, there's an unfortunate gap between the life expectancy and what we call as healthy life expectancy. There's a 10-year gap, which means that even as we are living longer, we are not living healthy lives. And the last 10 years, there's a 10-year gap, which means you live an average of 70 years today, but after the age of 60, people are living with multiple chronic ailments. And now today you have people living into the 80s and 90s, and certainly they're going to need a lot of assistance. So this is another area where industry, academia collaboration, there may be innovations coming out of institutions, but they have to be then scaled. And then, of course, the government has to also put it into the program, into the Ayushman Bharat, so that it's procured and distributed. So I think scientific institutions, firstly identifying the gaps, and again, that can be done with data, because I think when you look at data from health surveys, you can identify what is the percentage of people, who are blind or deaf, or, who are not mobile at a certain age, and so on. So we may need to also upgrade our surveys to include things like that, particularly for the extremes of age. And then similar we can say for drugs and diagnostics, but that's a very specialized area. But these are things I think where these institutions we can definitely. And then I think I would say also in the area of food, today I think one of the major risk factors for ill health is poor diets. And part of it is affordability of good diets, part of it is awareness. So there needs to be, we need to make systematic changes in many areas if we're going to change the food patterns from what is being consumed today to what one would, and NIN and other surveys, multiple surveys in India have shown that less than 10% of the population is actually consuming what would be considered a healthy, balanced diet today. And so there's an overconsumption of sugar, salt, and fat, and an under-consumption of protein. So I think these are probably things which are going to impact the health of everybody, and can be measured and tracked and monitored as well. Where institutions could, I'm sure several institutions here would be able to make. And then there are specific, I know that IIT, for example, is talking to VHS to set up collaboration on the medical side, where biomedical engineering, data, artificial intelligence, all of these things can be applied in regular clinical practice to see, and to test it through research, right, to see the impact.
So in fact, Professor Kamakoti was mentioning also, we are coming up with an MD PhD program. So these being set up in technological institutes give an interactive platform between clinicians and the scientists working in these areas. So like organically building up the collaboration to come out with the products. Now on the lines of local relevance, the problems, to find solutions to the local problems. I think if we can set up translational accelerators in the academic institutes, within the academic institutes, because many of us, then the scientists don't have to worry about the translation aspect, but they can be given the mandate to scout for the lab leads which can be worked upon to bring it to a level, the TRL advancement which we say, the technology readiness level for the market, where we can advance these lab scale discoveries to a level where they become marketable products or technologies, which can be of social relevance and as well as economical relevance.
So we'll just take a few audience questions at this point. So if you think you have a question, please just raise your hands and somebody will come to you with the mic.
Hi, I have a question about your thoughts about the question of basic science versus applied science. So when I was in school growing up and so on, almost all the science and the science heroes and so on that we were exposed to were basic scientists. I think the only engineer we heard of was Visvesvaraya maybe. These days, a lot of the excitement is, it's been touched on by some of you in terms of biomedical applications and so on.